The Milky Way looks balanced, a bright river of stars with darkness on both sides. But from here it's a tilted battlefield. One direction can send invisible gamma-ray firestorms that would rewrite life on Earth in seconds. The other hides a gravitational undertow pulling our solar system like driftwood. So what's really above and below the Milky Way? And which side is shaping our past, our motion, and our fate? From Earth, up and down feel like facts, stamped into our bones by gravity and horizon. Yet the moment you step into space, those words lose their anchor, until you choose a map. For our solar system, that map is the Milky Way itself, a flattened disk with poles, edges and hidden layers. We live inside that disk, offset from its centre, moving fast enough to turn centuries into footsteps. So when we ask what lies above and below the Milky Way, we are not asking for poetry. We are asking what surrounds us in the directions where starlight thins and where danger and guidance can hide. One side of this galaxy can answer with radiation, rare, violent flashes that cross the void like thrown spears. The other answers more quietly with gravity, an unseen current that steers stars, gas and entire galaxies. The night sky looks symmetrical, but symmetry is often a trick of distance and dim light. Above and below the bright band, the darkness is not empty. It is simply less familiar. There, the Milky Way's glow gives way to a different kind of evidence, written in energies our eyes never evolved to read. And there, motion itself becomes a clue, because our path is not random. It is being pulled. In this journey, we will rebuild up and down from first principles, then follow what those directions truly contain. We will move from the calm-looking poles to the high-energy sky, where the galaxy can shine without visible stars. We will trace the outlines of structures that appear only after patient measurement, shapes that hint at a restless past. Then we will pivot from photons to force, from sudden flashes to the steady mathematics of mass. Because the deeper question is not just what is out there, but what it does to us over time. What has brushed past our world before? What might arrive without warning? And what is already shaping our future? Above and below the Milky Way are not opposites. They are two frontiers that meet at our orbit. Between them, our solar system travels through a living galaxy, scarred, wrapped in a ghostly halo and threaded into a larger web. And as the camera pulls back, the familiar band becomes a boundary line, separating what we think we know from what we have yet to map. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will begin by dismantling the illusion of orientation, then follow energy upward and gravity downward, until the two stories converge. By the end, above and below will no longer mean empty space, but a set of forces with consequences. Up and down feel obvious on Earth because gravity gives everybody a vertical, and our inner ear quietly agrees. We learn orientation through floors, horizons, and falling objects, so above becomes instinct rather than calculation. In orbit, that certainty dissolves because there is no universal floor, only free fall. Astronauts float, planets tumble, and every direction can be renamed by whoever draws the map. Even the word level loses meaning when nothing is resting on anything else. Yet the Milky Way is not a random scatter of stars. It is a rotating disk of gas, dust, and billions of suns, shaped by angular momentum left over from its formation. A disk creates a natural reference plane, and that plane lets us rebuild orientation. When you picture the galaxy edge on, you can almost feel the geometry locking into place, thin, wide, and spinning. Astronomers call it the galactic plane. It is the midline of the Milky Way's disk as projected on our sky, traced by the densest concentration of stars and interstellar clouds. On a clear night far from city lights, it appears as a pale river of light, arcing from horizon to horizon. When we say above or below the Milky Way, we mean above or below that plane. It is not a moral up or down, just a shared coordinate choice grounded in structure. To measure it, we use galactic coordinates, a system built for the galaxy rather than for Earth's spin axis. Galactic longitude runs around the plane, tracing the disk's great circle as it wraps the sky. Galactic latitude measures angle away from the plane, positive to the north, negative to the south. The numbers are simple, but the idea is profound. We are defining direction using the Milky Way itself. This coordinate grid did not appear fully formed. It grew out of centuries of star catalogues, and it sharpened as radio astronomy revealed the galaxy's hidden skeleton. When astronomers mapped neutral hydrogen at 21 centimeters, the disk's shape became clearer even through dust. The modern galactic system formalized that insight, turning a luminous band into a precise reference frame. In a universe without signposts, the Milky Way becomes our compass. At latitude 0, the sky is crowded and bright. The disk packs stars into a luminous band, and dust lanes cut it into dark seams like ink spilled across starlight. In long exposure images, the band is granular, almost textured, with knots of star clouds and faint veils of nebulae. The brightness is not uniform because spiral arms and star-forming regions clump the light. Even the darkness is structured because dust is not evenly spread. At high latitude, the band thins and the sky looks cleaner and emptier. The star density drops, and individual points stand farther apart like distant lanterns across a wide field. The background becomes darker, not because space changes, but because fewer nearby stars fill the view. This is where the eye relaxes, and where intuition whispers that nothing is there. That whisper will turn out to be unreliable. The galactic poles anchor this system. The North Galactic Pole is the direction perpendicular to the plane on one side, a straight line out of the disk's midline. The South Galactic Pole points the opposite way, equally perpendicular, equally real. If the galactic plane is a sheet, the poles are the normals, pure geometry, clean and unforgiving. These poles are not mystical points. They are geometry tied to the Milky Way shape and rotation, and they remain meaningful even as the galaxy evolves. They give the galaxy an up and a down that any observer can share, whether they are on Earth or drifting between stars. In that sense, the poles are a kind of agreement between physics and language. They are where the disk stops dominating the view. But our viewpoint is not neutral. The solar system is not at the centre of the disk, and not exactly in its middle layer, so our sky is not a perfectly balanced panorama. Every map we draw is filtered through location, and location is a bias. We do not look outward from a throne at the centre, we look outward from a suburb. We live in the Orion Arm, also called the local spur. It is a minor bridge between larger spiral arms, rich in star-forming clouds and threaded with dust and molecular gas. It is home, but it's not a privileged location. Nearby are stellar nurseries, older clusters, and the faint haze of interstellar material that will become future stars. Our neighbourhood is active, but it is not the galaxy's main stage. From here, the galactic centre lies far away. The distance is about 8 kiloparsecs, roughly 26,000 light-years, a span so large that even light needs millennia to cross it. In that direction sits Sagittarius A, the compact radio source that marks the central supermassive black hole. We orbit that centre with the rest of the disk, carried by a rotation we barely feel. The motion is swift on a galactic scale, yet it is slow compared to a human life. This orbit is not a perfect circle. The disk's gravity, spiral structure, and passing clouds gently perturb trajectories over time, nudging stars like boats on a broad current. Still, the overall pattern is clear. The Milky Way rotates, and the plane is the stage of that rotation. The plane is where most of the mass we can see resides. It is also where most of the dust hides what lies beyond. We also sit slightly off the midplane. The Sun is displaced by tens of parsecs from the disk's central layer, a modest offset that becomes meaningful when you think in terms of density. That offset is small compared to the galaxy, but it makes above and below physically meaningful. It means our horizon through the disk is not exactly symmetrical. Even a small vertical shift changes how much gas and dust lies in each direction. If you could draw the Milky Way as a thin sheet, we would not be exactly on the sheet. We would hover a little to one side of it, like a bead slightly above the centerline of a spinning record. Even our definition of the plane is an average through messy structure. The disk has ripples, warps, and local corrugations, so the midline is a best-fit surface rather than a perfect mathematical plane. So when we look toward the North Galactic Pole, we are looking out of the disk's dense midline. When we look toward the South Galactic Pole, we look through a different thickness of gas and dust. The two directions are not identical because we are not perfectly centered. The difference is subtle in visible light, but it becomes important when you measure faint backgrounds and diffuse glow. This is where the illusion begins. The night sky suggests symmetry, stars above and stars below, darkness between, as if the cosmos were a balanced dome. The galactic coordinate grid suggests order, a clean plane and two clean poles. It tempts us to believe the galaxy is a tidy disk with tidy edges. But the Milky Way is not a diagram, and its boundaries are not sharp. Then the data breaks that calm picture. The disk is bright in visible light because stars and nebulae crowd the plane, and because our eyes are tuned to that band. The poles look quiet in visible light because dust and stars thin out, and because fewer bright objects compete for attention. The calm is partly real, and partly a trick of the detector. What looks empty is often just faint in the wrong wavelength. Quiet does not mean empty. Away from the plane, the galaxy's hidden layers become easier to detect, because the glare of the disk fades and the dust curtain thins. The poles are windows into processes that do not glow like starlight. When you remove the bright foreground, the background can finally speak. The question becomes, what is the galaxy doing when it is not making stars? In gamma rays, the sky above and below the disk can flare with structure, as if invisible weather were moving through the halo. Gamma rays are the highest energy photons, born when particles are accelerated to extreme speeds or when matter and radiation collide violently. They do not arrive as a gentle glow in the mind's eye. They arrive as statistics, counts, energies, and maps built from patient observation. In X-rays, hot plasma fills volumes that optical telescopes barely hint at, because temperatures of millions of degrees shift emission into higher energies. Such plasma can be produced by supernova shocks, stellar winds, or large-scale outflows that heat gas as it expands. In radio, magnetic fields sketch arcs and loops that ignore the neatness of the starband. Radio polarization can even reveal field directions, turning the sky into a map of invisible forces. The paradox is immediate. The place that looks busiest can hide what is most ordinary, long-lived stars and cold clouds that dominate by number and mass. The place that looks blank can hide what is most extreme, fast particles and violent outflows that announce themselves only in high-energy bands. Our eyes, evolved for daylight and firelight, are not impartial instruments. They are narrow-band sensors in a broadband universe. High-energy radiation does not respect human intuition. Gamma rays can cross the galaxy without caring about dust lanes, because dust grains that block visible light are almost irrelevant at those energies. Cosmic rays can arrive from directions that look empty, because their sources are not bright invisible light. Many cosmic rays are charged particles, so magnetic fields bend their paths until the original direction is blurred. The sky becomes a scrambled message that must be decoded. Above the plane, there can be bubbles of hot gas and shock fronts, expanding like cavities carved into the halo. Below the plane, there can be mirrored structures, shaped by the same central engine, even if the symmetry is imperfect. The Milky Way can breathe through its poles, venting energy into its halo. When you imagine it, picture a vast disk exhaling into darkness. Slowly, relentlessly, over millions of years. We are used to thinking of the galaxy as a flat city of stars, but a disk is only the beginning of the story because gravity does not stop at the bright band. A halo surrounds it, and that halo holds heat, magnetism, and mass that does not shine. The halo is not a decorative shell, it is part of the galaxy's working machinery. The first mystery is what is raining down from above. Some of it is radiation, photons at energies that can damage life and electronics, and that can penetrate materials that visible light cannot. Some of it is particles, atomic nuclei accelerated to near-light speed, arriving as cosmic rays. They strike atmospheres, generate cascades of secondary particles, and quietly add ionization to the air. Even when we do not notice the planet is being bombarded, those messengers are not just background noise. They can change chemistry in atmospheres and in clouds, because ionization can break molecules and open new reaction pathways. They can seed ionization, trigger reactions, and leave signatures in rocks and ice. In the right conditions, they can influence how clouds conduct electricity, or how complex molecules survive in interstellar space. The sky is not merely light, it is a stream of physical interactions. The second mystery is what is pulling from below. Gravity is not a beam you can point at the plane. It is a field produced by everything with mass, including what we cannot see. It acts continuously, shaping orbits with silent persistence. If radiation is the galaxy's weather, gravity is its terrain. The stars in the disk contribute to that pull. The gas contributes, even when it is cold and dark, because mass does not need to glow to matter. but the largest share may come from dark matter, a halo of mass inferred from motion rather than light. The evidence is dynamical, not photographic. We see its influence in how fast stars orbit and how the outer disk refuses to slow down. Our solar system moves through this combined field. We orbit the galactic center, but we also bob up and down through the plane over long timescales, like a slow oscillation through a crowded lane. That vertical motion is a clue that the disk has thickness and that the halo has weight. The restoring force is gravity, and the period encodes the mass distribution. Motion becomes measurement. If the galaxy were only what we see, the motions would not match. Rotation curves stay high where visible matter thins out, a mismatch first recognized as data improved and expectations failed. Something unseen deepens the gravitational well, and it shapes the paths of stars like ours. This is not a small correction, it is a dominant component of the galaxy's mass budget. So above and below are not empty directions. They are routes for energy and for force, and they connect the bright disk to the faint halo. One side can deliver high-energy radiation that arrives without warning, because the sources can be distant and the photons travel straight. The other side can hide the mass that steers our orbit and sets our long-term stability. The same coordinate system that defines up also points toward hazards and hidden structure. This is why the question matters. Our sense of safety is built on local experience, day and night, ground and sky, where threats are visible and distances are small. But the Milky Way is an environment, and environments have hazards and currents. The galaxy has a climate of particles and fields, operating on timescales that dwarf civilizations. If we live inside it, we should ask what it is doing around us. The disk feels like home because it is bright and familiar. The poles feel like void because they lack the starband, and because our eyes read darkness as absence. Yet the poles may be where the galaxy's most dramatic feedback is easiest to trace. When the disk's glare fades, faint structures emerge, edges, lobes, and diffuse halos that would otherwise be washed out. Sometimes the quiet sky is quiet only because we are listening with the wrong sense. The more we map the sky in every wavelength, the less symmetrical it becomes. Visible light shows a thin, crowded plane, a bright belt that dominates the human view. Gamma rays and X-rays reveal lobes, chimneys, and diffuse glow extending far above and below. Radio maps add filaments and loops, hinting at magnetized structures that span enormous distances. Each band is a different truth, and the truths do not always align. Even the word above becomes loaded. Above the plane can mean closer to the North Galactic Pole, but it can also mean closer to the halo's high-energy structures that appear to rise from the center. Below can mean the opposite direction, but also a different path through the disk's uneven dust. Our vocabulary is simple, while the galaxy is layered. The challenge is to keep the words, but deepen what they point to. Our position makes the puzzle personal. We are 8 kiloparsecs from the center, riding in the local spur surrounded by the ordinary glow of a spiral suburb. We are tens of parsecs off the midplane, already slightly tilted into one hemisphere. That small displacement changes the column of material we look through, and it changes what we can detect. Perspective is physics, not just viewpoint. From this offset seat, we ask a dangerous question. What events in the halo can reach the disk, and how often, and with what consequences for planets embedded in the thin layer of stars? What hidden mass beneath the starlight controls our vertical oscillation and our future trajectory? Are the poles merely directions on a grid, or are they pathways for the galaxy's most energetic exchanges? If the disk is a city, what is happening in the dark sky above its rooftops? The answers will not come from one kind of telescope. They will come from stacking maps of photons and particles and comparing them to the motions of stars and gas. They will come from treating the Milky Way as a dynamic system, not a backdrop. The story is written in spectra, in arrival directions, and in the slow drift of stellar orbits. To read it, we have to combine patience with precision. Two forces will guide this journey. The first is high-energy radiation, gamma rays and cosmic rays that trace violent acceleration, shocks and interactions that can occur far from any bright star. The second is gravity, from visible matter and from dark matter, shaping every orbit and every escape. One force announces itself in bursts and glows, the other works in silence, yet it never stops. If we can define up and down using the galactic plane, we can ask what truly lives in those directions. If we can locate ourselves precisely, we can separate local illusion from galactic structure. If we can read the poles correctly, we can see the Milky Way's hidden engines. Orientation becomes more than navigation. It becomes a way to expose what the bright band conceals. Now we leave the comfort of the bright band and follow the evidence into the quiet-looking sky. We track the gamma-ray signatures above and below the disk, and we ask what could generate them. Then we follow the pull of gravity into the unseen mass that holds the galaxy together. Up and down will stop being metaphors and start becoming measurements of energy, of matter, and of the forces that shape our home. Above and below the galactic plane, the sky looks calmer, almost rinsed clean of clutter, but the galaxy does not end. Chapter 1 gave us a coordinate grid and 2 poles, and it taught our eyes where up and down are on a cosmic map. Now we use that geometry to describe the Milky Way as a layered machine, with parts that spin, heat, cool, and exchange matter. From Earth, the bright band feels like the whole story, yet the poles point into structure that is simply harder to see. Start with the thin disk, the luminous ribbon that trained our eyes long before telescopes had names for it. It is where cold gas concentrates, where dust is thickest, and where stars still form in clustered nurseries. Its scale height is about 300 parsecs, only a few hundred light-years of vertical thickness, which is remarkably thin for something spanning tens of thousands of light-years across. Most of the Milky Way's visible light is packed into this narrow layer, because young, massive stars burn bright and die fast in the same neighbourhoods where they were born. Visually, the thin disk is a city seen edge-on, with bright avenues of starlight and dark lanes of soot. Those dark lanes are not empty gaps, but dust clouds, micron-sized grains of silicates and carbon compounds that absorb optical light and re-radiate it in infrared. In wide-field images, the dust looks like ink spilled across the band, and it is doing real physics, not just adding drama. Dust cools gas by radiating energy away, and it provides surfaces where molecules can form, including the H2 that marks the coldest star-forming regions. Even our own solar system carries the chemical fingerprints of this dusty factory. Inside the thin disk, gravity and rotation keep gas orbiting in a flattened sheet, and the balance is never perfectly calm. Differential rotation means the inner galaxy goes around faster than the outer parts, so material is constantly being sheared and stretched. Spiral arms are not rigid objects, but patterns, density waves or transient features that gather gas and trigger star formation as clouds enter them. As gas compresses, it can cool, fragment and collapse, and the result is an assembly line of stars that lights up the arms like a moving marquee. Supernovae and stellar winds inject heat and turbulence into the surrounding interstellar medium, and the energy arrives in bursts. A single core collapse supernova releases about 1051 ergs, enough to drive a shock front through surrounding gas and carve a hot bubble. Massive stars also blow winds for millions of years before they explode, adding momentum and sculpting cavities that later supernovae expand. The disk is not quiet. It is regulated violence on a repeating cycle, where collapse and disruption alternate like breathing. That cycle is visible if you know what to look for, even from far away. Radio maps trace cold hydrogen through its 21 centimeter emission, revealing clouds and filaments that optical eyes never see. Infrared surveys show warm dust glowing where ultraviolet light hits it, outlining star-forming regions like embers under ash. In X-rays, hot gas in supernova remnants shines as thin shells and knots, marking where shocks heat plasma to millions of degrees. The thin disk is a multi-wavelength machine, and each band reveals a different gear. Above the thin disk sits the thick disk, older and dynamically hotter, like a puffed-up version of the same rotating system. Its scale height is about 1 kiloparsec, several times thicker than the star-forming layer, and it contains stars that spend more time away from the midplane. Thick disk stars tend to be older and more metal-poor than thin disk stars, meaning they formed when the galaxy had fewer heavy elements to build with. Their orbits are not as circular, and their vertical motions are larger, suggesting a past of heating, mergers, and long-term stirring. Dynamically hotter sounds abstract, so translate it into motion you can imagine. In the thin disk, many stars move in relatively orderly, nearly circular paths, like cars on a highway with small lane changes. In the thick disk, the same rotation is present, but the stars bob up and down more strongly and drift inward and outward more noticeably. That extra random motion is a memory of past gravitational kicks, preserved for billions of years because stars do not easily lose orbital energy. The thick disk is not just thicker, it is a record of agitation. The thick disk matters because it is a fossil record of how the Milky Way grew, and fossils are most valuable when they are difficult to fake. It hints that the galaxy did not form as a single smooth collapse, quietly settling into a thin, cold sheet. Instead, it was shaped by accretion, by satellite interactions, and by internal instabilities that can heat stellar orbits over time. Some scenarios propose early turbulent disks that later cooled, while others emphasize mergers that puffed up an existing population. Above and below the plane, the thick disk becomes a bridge between the bright city and the faint outskirts. Historically, this layered picture emerged slowly, because our viewpoint from inside the disk makes geometry deceptive. Early star counts by astronomers like William Herschel suggested a flattened system, but dust obscuration distorted the apparent distribution. In the 20th century, radio observations pierced the dust, and the 21 centimeter line revealed the disk's spiral structure and gas. Later, large surveys of stellar motions and chemistry made the thick disk unmistakable as a distinct component. Each improvement in technique turned the Milky Way from a blurry glow into an engineered structure. Toward the center, the disk gives way to the bulge and bar, where the density of stars rises and the gravitational potential steepens. The bulge is a dense central concentration of stars mixed in age and chemistry, with populations that include very old stars and others that formed later. The bar is an elongated structure that channels gas inward and reshapes stellar orbits, and it is now considered common in disk galaxies. This central region is where gravity is steep, where orbits precess, and where the galaxy's engine room sits behind curtains of dust. Visually, the center is a bright knot in infrared, because dust that blocks visible light becomes almost transparent at longer wavelengths. In optical images, the bulge is largely hidden, and the plane looks like a broken band. In infrared maps, the bulge swells into view, and the bar appears as a stretched glow, tilted relative to our line of sight. It is a reminder that what looks like absence can be a wavelength problem, not a physical void. The galaxy's core is not dim, it is veiled. The bar is not just a shape, it is a conveyor belt, and its physics is tied to resonances in rotating systems. As stars and gas respond to the bar's gravitational torque, angular momentum can be redistributed, allowing gas to lose orbital energy and drift inward. That inflow can pile up in rings or feed the inner few kiloparsecs, where densities rise and star formation can flare. The same torques can also rearrange stellar orbits, building structures that look like boxy or peanut-shaped bulges in other galaxies. A bar is a mechanism, not a decoration. It can also influence how material is launched out of the plane, because concentrated star formation and central activity create pressure and heat. If the Milky Way ever lit up its halo, the central regions are a prime suspect, simply because they can concentrate energy injection. Even without a dramatic outburst, the inner galaxy can drive fountains of hot gas that rise and fall over long timescales. The engine room does not need to explode to matter, it only needs to persist. In galaxies, persistence can be as consequential as violence. Beyond the disks and bulge, the stellar halo begins, and the density of stars drops so far that emptiness becomes an illusion of statistics. It is sparse, made of old stars and globular clusters on eccentric tilted orbits, many of which plunge through the inner galaxy and back out again. Its stars are so spread out that the sky can look empty even when it is not, because the average separation becomes enormous. Yet the halo is real, and it surrounds the bright disk like a faint ancient mist. Streams and shells reveal that many halo stars arrived through mergers, and those structures are among the most persuasive evidence for hierarchical growth. When a smaller galaxy falls in, tidal forces stretch it into long ribbons, and the stars continue along similar orbits for billions of years. Over time, the streams phase mix and fade, but some remain coherent enough to map like trails in snow. The halo is a graveyard of disrupted companions, still not fully mixed, and every stream is a sentence in the Milky Way's autobiography. Globular clusters add another layer of context, because they are dense, old star systems that orbit far from the plane. Some likely formed in the early Milky Way, while others may have been captured along with accreted satellites. Their stellar populations preserve chemical signatures, and their orbits can hint at their origins. In visual terms, they are like lanterns hung in the dark, marking the shape of a region that would otherwise be invisible. Even a sparse halo can be traced if you have enough lanterns. Yet even the stellar halo is only a tracer, not the main mass, and this is where the galaxy becomes stranger. The dominant structure is the dark matter halo, extending far beyond the visible galaxy, and it is inferred rather than photographed. It reaches out to hundreds of kiloparsecs, enveloping the Milky Way and its satellites, and it provides the gravitational scaffold that keeps the system bound. We infer it from motions, from rotation curves, and from the dynamics of streams that would otherwise disperse. The galaxy's light sits inside a much larger gravitational architecture. The logic is simple, even if the conclusion is unsettling. If you measure how fast stars and gas orbit at different radii, you find that the speed does not fall off as quickly as visible matter alone would allow. Something unseen must add mass at large distances, keeping orbital velocities high. In the Milky Way, this inference is supported by the motions of satellite galaxies and by the way stellar streams curve through space. Dark matter is not an optional add-on. It is the framework that makes the observed motions possible. This is the first correction to the night sky illusion. The bright disk is not the whole galaxy, and its edge is not a boundary, even if it feels like one to the naked eye. Above and below the plane, gravity still binds material to the Milky Way, and the system extends far beyond the band of starlight. The poles are not exits, they are directions through a larger atmosphere, where faint components dominate the mass and the long-term evolution. That atmosphere is the circumgalactic medium, the CGM, and it is one of the most important structures you cannot see. It is tenuous ionized gas surrounding the galaxy, extending through much of the dark matter halo, and it forms an interface between the disk and intergalactic space. Typical temperatures run from about 100,000 to 1,000,000 Kelvin, which is hot enough to strip electrons from atoms. At those temperatures, hydrogen is mostly ionized, and the gas is hard to see directly, because it emits little visible light. The CGM is not a uniform shell, and that complexity matters for both physics and imagery. It likely includes hotter, more diffuse plasma, cooler clumps, and intermediate temperature gas where ions like OVIG are abundant. Some regions may be enriched by metals from past outflows, while others may be more pristine, carrying the chemical simplicity of the intergalactic medium. In simulations, it appears as tangled filaments and patchy clouds, threaded through a larger hot background. The halo is not smooth, it is textured. The CGM is detected by its fingerprints on other light, which turns distant objects into probes. When a distant quasar or galaxy shines through it, the CGM leaves absorption lines in the spectrum, removing precise wavelengths like a barcode. Oxygen in the overstate is a key tracer of gas around a few times 10 to the 5th Kelvin, because that ionization state is most common at those temperatures. Hotter components can glow in soft X-rays, revealing million-degree plasma that is too thin to shine brightly. We see the CGM the way we see wind in dust, by its effects. There is a quiet elegance to this method, and it has a history of transforming astronomy. Spectroscopy turned starlight into chemistry in the 19th century, when absorption lines revealed that the same elements exist on Earth and in the Sun. In modern halo studies, the same technique is aimed outward, using background beacons to sample the space between. Each quasar sight line is a narrow drill core through the galaxy's outskirts, measuring temperature, velocity, and composition in a medium that would otherwise be invisible. The CGM becomes a map made from shadows. This is the second correction to the illusion. Space above the disk looks empty because it is thin, not because it is nothing, and thin things can still matter. The CGM can hold a large fraction of the Milky Way's normal matter, the baryons made of protons and neutrons. It is a reservoir for the so-called missing baryons, matter expected from cosmology, but difficult to count in stars and cold gas. The galaxy's mass budget is written in faint ions and diffuse X-ray photons, and the accounting changes our sense of what a galaxy is. In plain terms, the Milky Way is not just what shines, it is also what weighs. If baryons are missing from the disk, they may not be missing at all, but hiding in a hot, low-density halo that is difficult to inventory. That matters because baryons are the raw material for future star formation, and because metals carried into the CGM record the galaxy's past. Every enrichment event, Every outflow and every recycled cloud leaves a chemical trace. The halo is a ledger, even when it looks like fog. The CGM is also an energy system, not a static mist, and its state reflects a competition between heating and cooling. Gas can fall in from the intergalactic medium, cooling and feeding the disk over time, especially along filaments that connect galaxies on large scales. Gas can also be driven out by supernova feedback and central activity, heating and enriching the halo as it expands. The Milky Way can breathe, cycling baryons between disk and halo, and the cycle can last for billions of years. Above and below the plane, we are watching that circulation from inside, like living within a weather system. Cooling is not just a metaphor here, it is a measurable process with consequences. Hot gas radiates energy through emission lines and bremsstrahlung, and as it cools, it can condense into clouds that become visible in different traces. If cooling is too efficient, the disk would be flooded with fuel and star formation would surge, changing the galaxy's appearance. If heating dominates, the disk could starve, and the bright band would slowly dim. The CGM helps set the pace of the Milky Way's future. The poles matter because they are cleaner sight lines through this layered structure, and cleanliness is a form of power in astronomy. Looking along the plane, dust extinction blocks optical light and confuses distance estimates, because reddening and dimming mimic greater distance. Star counts pile up, and overlapping clouds hide what lies behind them, turning the line of sight into a crowded hallway. Looking toward the galactic poles reduces that crowding and reduces the dust column, so faint structures have a chance to stand out. The background universe becomes easier to see, and the halo becomes easier to isolate. Visually, the difference is striking even in simple all-sky maps. Along the plane, the Milky Way is bright, mottled and scarred by dark rifts, and it dominates the frame like a glowing river. Toward the poles, the sky becomes a quieter gradient, with fewer foreground stars and a clearer view of distant galaxies. That quietness can feel like emptiness, but it is simply a lower surface brightness foreground. The poles are windows, not voids. This is why high-latitude surveys became so powerful, especially as detectors improved and sky coverage expanded. They can measure faint diffuse emission without the disk's glare dominating the signal, and they can push to lower surface brightness where the halo lives. They can use background quasars as flashlights to probe intervening gas, building statistical maps from many narrow beams. They can map halo stars and streams with less confusion from the dense midplane, allowing the fossil record of mergers to emerge. The poles are not special because of mysticism, they are special because of geometry. Geometry is only the start because the halo is threaded with invisible forces that change how gas moves. The Milky Way has a large-scale magnetic field, ordered on kiloparsec scales and tangled on smaller scales, and it permeates both disk and halo. We infer it from polarized radio emission and from Faraday rotation of background sources, where the plane of polarization twists as light passes through magnetized plasma. Magnetic fields do not just decorate the galaxy, they guide charged particles and influence how gas can flow. In a plasma, fields can be as real as walls. The field is not perfectly uniform, and that irregularity is part of its character. Turbulence in the interstellar medium can tangle field lines, while large-scale rotation can stretch and order them through dynamo action. In observations, this shows up as a mix of coherent patterns and noisy fluctuations, depending on the scale you examine. When you look at radio polarization maps, you're effectively seeing the galaxy's invisible grain, like wood fibers revealed by varnish. The halo has structure you can feel, even if you cannot see it directly. Cosmic rays are part of that story, and they carry pressure that can compete with ordinary gas. They are high-energy charged particles, mostly protons and nuclei, accelerated by shocks and energetic environments such as supernova remnants. Because they are charged, magnetic fields scatter and confine them, especially near the disk, and that confinement lets their energy density build up. Their pressure can become comparable to thermal gas pressure in some regions, which means they can push on plasma over large distances. Together with magnetic tension, they can help lift material upward against gravity. This is the third correction to the illusion. Above and below the plane, the galaxy is not only gas and stars, even though those are the components our eyes prefer. It is also fields and particle populations that do not show up in ordinary starlight, yet they store energy and transmit forces. These components can transfer momentum, drive turbulence, and shape outflows, changing the halo's density and temperature over time. They can turn the halo into a dynamic interface between the disk and intergalactic space. where the rules of motion are written in magnetism. When star formation and supernovae inject energy into the thin disk, the energy does not always stay there, because hot gas is buoyant and seeks lower pressure. Hot plasma can rise, carving chimneys through lower density regions, and those channels can connect the disk to the halo-like vents. Magnetic fields can guide flows along preferred directions, and cosmic rays can add a steadier push that persists after the hottest gas cools. The result can be a galactic wind, moving preferentially perpendicular to the plane, because that is where the density drops fastest. The poles become the natural direction for escape and exchange. In imagery, you can picture it as a slow, luminous exhalation. Though most of the light is outside the visible range, hot gas may glow faintly in X-rays, while cooler and trained material can show up in ultraviolet absorption or in radio emission from neutral clouds. The wind is not necessarily a single stream, but a layered flow with hot cores and cooler fragments, shaped by instabilities. Over millions of years, such flows can carry metals into the CGM and alter its chemistry. A galaxy's breath leaves stains. At the same time, the halo is not only an outflow destination, and it is not only a dumping ground. It is also the route for infall, as cooler clouds and filaments rain back toward the disk, returning mass that was lifted earlier or arriving from outside. High-velocity clouds in the Milky Way's halo may be part of this process, moving at speeds that do not match simple disk rotation. Some are enriched, suggesting recycled material from the disk that was lofted and is now returning. Some may be more pristine, hinting at fresh accretion from beyond the galaxy's immediate environment. This back and forth matters because it sets the long-term fuel supply for star formation, and it shapes the disk's chemical evolution. If infall brings in low metallicity gas, it can dilute the disk and extend star formation into the future. If outflows dominate, the disk can lose metals and mass, changing the composition of later generations of stars. The Milky Way's present appearance is a snapshot of that balance, captured mid-cycle. From inside, we feel the stability, but the system is always in motion. So the Milky Way's architecture is layered and coupled, and each layer speaks to a different timescale. Thin disk forms stars and launches energy, and it changes on timescales of millions to billions of years. Thick disk preserves an older, heated population and hints at past disruptions that may be difficult to reconstruct in detail. Bulge and bar reshape orbits and funnel gas inward, influencing central star formation and the distribution of angular momentum. Stellar halo records merges in streams and clusters, while dark matter halo sets the gravitational stage far beyond the light. Wrapped around all of it, the CGM holds ionized gas at extreme temperatures, and it is both storage and transit. It stores baryons, carries metals, and mediates the galaxy's long-term fuel supply, even when it's too faint to image directly. It is where feedback and accretion compete, and where the disk's history is written in chemistry that can be read through spectra. Above and below are not directions into nothing, even if the sky looks blank at first glance. They are directions into the Milky Way's extended body, where the galaxy becomes more than its starlight. From our solar system, this matters because we live inside the thin layer, embedded in its dust and its crowded star fields. The disk's extinction and confusion can hide the halo's faint signals, and they can bias our intuition about what is normal in a galaxy. The poles offer a way to separate local clutter from global structure, because the path through the disk is shorter and cleaner. If we want to know what lies above and below, we must look where the disk interferes least, even if that view feels deceptively empty. The cleanest windows are also the most misleading to the naked eye, and the halo is not always quiet, even when it resembles a ghostly atmosphere in our maps. If it is a tenuous envelope, it can still be lit by sudden, violent events, and those events can leave signatures that persist long after the trigger fades. Some events are slow, like sustained winds over millions of years that gradually inflate bubbles and transport energy outward. Others are sharp, like bursts of particle acceleration that leave high-energy afterglows, or rapid injections of energy that ripple through the CGM. The next step is to ask what can make the halo shine in gamma rays, and what that glow would reveal about the engine beneath. Yet the Milky Way is not a random scatter of stars, and it is not merely a backdrop for constellations. It is a disk of fire embedded in a halo of ghosts, with gravity as the skeleton and plasma as the weather. When we look away from the bright band, we are not looking away from the galaxy, we are looking into its larger body. The poles point into a realm of thin gas, ancient stars, and invisible forces that still shape the future. Now we leave the comfort of the bright band and follow the evidence into the quiet-looking sky. Now we leave the comfort of the bright band and follow the evidence into the quiet-looking sky. The poles look empty in starlight, yet they can glow in the hardest photons, light so energetic it feels almost like a different substance. Gamma rays are electromagnetic radiation at the highest energies, with the shortest wavelengths and the least patience for matter. They do not behave like heat or colour, so intuition fails when the photon carries particle-like violence. A gamma ray is still light, but it is light with enough energy to ionize and shatter molecules. In practical terms, it can knock electrons loose, break chemical bonds and start cascades of reactions that biology cannot easily repair. In space, it travels straight, ignoring dust that blocks visible bands and confuses distance. If it reaches your detector, it points back to extreme physics, not to gentle illumination. The sky becomes a map of accelerators, collisions, and rare catastrophes. To place it on the spectrum, think in energies rather than colours. Visible photons are a few electron volts, while gamma rays begin around millions of electron volts and climb to trillions. That scale matters because energy per photon changes the interaction rules. Gamma rays are counted one by one like impacts, not like a warm glow. Even the language shifts because we start describing particle processes rather than optics. On Earth, we survive because the atmosphere is a shield that turns gamma rays into cascades. High-energy photons strike air molecules, create electron and positron pairs, and feed showers of secondary particles. Those secondaries radiate again through bremsstrahlung, making more high-energy photons that continue the chain. Most of that energy is absorbed high above the ground, long before it can reach lungs or oceans. The same protection also blinds ground telescopes, forcing gamma-ray astronomy into space. Early researchers could infer high-energy radiation indirectly, but direct mapping required instruments that lived above the air. In the early space age, detectors were simple counters, and even confirming a cosmic signal was difficult. Each improvement in altitude, shielding, and background rejection widened the window by degrees, so the gamma-ray sky was opened by satellites that could live above the air. The Compton Gamma Ray Observatory carried Egret and made the first detailed all-sky maps, turning scattered detections into a coherent survey. Egret's catalogues revealed bright pulsars, a glowing galactic plane, and a puzzling population of unidentified sources. Later, Agile refined timing and localization, especially for fast transients and pulsars. Fermi, with the Large Area Telescope, turned gamma rays into a precision survey and a monitor for sudden flares. These instruments do not take pictures the way optical cameras do. They count individual photons, measure their energies, and reconstruct directions statistically over long exposures. A gamma ray enters, converts into an electron-positron pair in dense material, and those tracks are measured layer by layer. From the geometry of the tracks, the original direction is inferred, but never perfectly. The maps are built from probabilities, backgrounds, and careful subtraction of charged particle contamination. In gamma rays, the universe is not painted, it is accumulated, minute by minute, photon by photon, with uncertainty carried forward like a shadow. A bright source is not a bright pixel, but a persistent excess above a modeled sky. A faint structure is a pattern that survives repeated tests against instrumental noise. The result feels almost forensic, as though we are reconstructing an event from fragments. The first lesson is definitional and unsettling. Gamma rays are not a separate substance, only the extreme end of the electromagnetic spectrum. Their energies can range from millions to trillions of electron volts, far beyond visible photons. At those energies, a single photon can carry the punch of a speeding atom. It is still massless, still travelling at light speed, yet it can deliver its energy in a single damaging act. The second lesson is about production, because gamma rays are not usually emitted by calm matter. They are produced when charged particles are accelerated and then forced to radiate, or when particles collide and create new particles. They can also appear when matter meets antimatter, converting mass directly into photons. Every mechanism implies a different environment and a different kind of danger. Every mechanism also leaves a different spectral fingerprint, an energy distribution that hints at what happened. Start with supernova remnants, the expanding shock waves of dead stars. Their shocks can accelerate protons and electrons through repeated crossings, a process called diffusive shock acceleration. Magnetic turbulence scatters particles back and forth, letting them steal energy from the bulk flow. Each crossing is a gamble that can pay out, and over thousands of years, a remnant becomes a natural particle accelerator. In radio and X-rays, we see the synchrotron glow of fast electrons, and in gamma rays, we test whether protons are accelerated too. Electrons accelerated in these shocks can make gamma rays by inverse Compton scattering. A fast electron collides with a low-energy photon and boosts it upward into the gamma band. The seed photons can be starlight, infrared glow from dust, or the cosmic microwave background. Even in thin halo regions, that photon field is everywhere, waiting to be upgraded. Inverse Compton is a simple idea in plain language. The electron gives some of its speed to light. Protons and heavier nuclei tell a different story, because they can collide with gas and create pions. When a cosmic ray proton hits an interstellar proton, the collision can produce neutral pions. Neutral pions decay almost instantly into 2 gamma rays, with a characteristic spectral signature. This channel ties gamma emission to gas density, even when the gas is tenuous. It also ties gamma maps to the otherwise invisible distribution of hydrogen and molecular clouds. Pulsars add a second class of accelerators, compact and relentless. A neutron star spins with a strong magnetic field and generates enormous electric potentials. Particles are ripped from the surface or magnetosphere and accelerated along curved field lines. Curvature radiation and magnetospheric cascades can produce gamma rays with sharp periodic timing. The pulse is not just a blink, but a rotating lighthouse beam shaped by geometry and relativistic effects. In the magnetosphere, a single gamma ray can trigger pair creation in the intense field, spawning electrons and positrons that radiate again. This multiplication builds a cascade, and the cascade shapes the spectrum we observe. Timing becomes a tool as powerful as imaging, because periodicity can identify a source even when localization is imperfect. When the period is stable, it is like a signature written into the photon stream. Some pulsars are embedded in pulsar wind nebulae, where the wind slams into surrounding material. The termination shock accelerates electrons to extreme energies and fills a bubble with relativistic plasma. Those electrons again upscatter ambient photons through inverse Compton processes. The result can be bright gamma emission that extends beyond the visible nebula. In visuals, the nebula can look like a ghostly halo, larger in high energy than in starlight. Black holes and their jets push the story to larger scales and higher stakes. In microquasars and active galactic nuclei, accretion disks feed compact objects and launch collimated outflows. Shocks and magnetic reconnection in jets accelerate particles, producing gamma rays through synchrotron-related processes and inverse Compton scattering. When the jet points toward us, beaming can make the flare appear sudden and overwhelming. The brightness is not only power, but alignment, geometry acting like a magnifying glass. These are the established engines, powered by gravity and rotation and magnetic fields. But gamma rays also invite speculation, because they can be produced by new physics. Dark matter, if it is made of particles, could annihilate with itself or decay into standard particles. Those products could yield gamma rays directly or through cascades, leaving a faint, spatially extended signal. The appeal is clear: gamma rays travel straight, so a diffuse glow could trace where invisible mass is densest. This remains a hypothesis, not a discovery, and the narration must hold that line. The challenge is that ordinary astrophysical sources can mimic many expected signatures. Pulsars, unresolved remnants, and diffuse emission can pile up into confusing backgrounds. In gamma rays, uncertainty is not a flaw, it is part of the measurement. The question becomes methodological: what can be separated cleanly and what remains entangled? Now connect this to the central question about above and below the Milky Way. In visible light, the plane dominates because stars and dust concentrate there. In gamma rays, the plane is bright too, but the high-latitude sky refuses to go dark. The halo contains energetic particles and target photons, so interactions continue far from the crowded disk. What looks like emptiness is often just low density spread across enormous distance. Cosmic rays do not stay confined to the thin star-forming layer. They diffuse along magnetic fields, scatter on turbulence, and leak into the thick disk and halo. Their motion is not a straight flight, but a random walk guided by invisible structure, field lines, waves, and irregularities. Energetic electrons and protons can fill volumes that look empty in optical surveys. Above and below the plane, the galaxy still has a weather of particles. Even low-density gas can matter when the volume is enormous. A single cubic centimetre may hold almost nothing, yet a path length of kiloparsecs adds up. Cosmic ray collisions integrated over that depth can produce measurable gamma emission. The halo is thin, but it is not negligible. In a map, this appears as a faint wash that becomes meaningful only after careful modelling. The interstellar radiation field also extends above and below, though it changes with height. Starlight weakens away from the disk, but infrared and the cosmic microwave background remain. For inverse Compton scattering, the CMB becomes a universal target that never turns off. Energetic electrons in the halo can therefore light up the gamma sky without any dense clouds. In that sense, the halo is never truly dark, because the universe supplies its own backlight. This is why gamma rays can arrive from directions that look like void. The photon does not care whether the source region has stars you can see. It cares whether particles are accelerated and whether targets exist for collisions or scattering. The emptiest looking regions can host the most extreme physics, because emptiness can be the stage. If you could see in gamma rays with your eyes, the poles would not feel quiet at all. The Milky Way's halo also carries signatures of large-scale outflows and past activity. If the central regions drove winds or inflated bubbles, those structures can contain cosmic rays and magnetic fields. Gamma rays can trace their edges through inverse Compton emission or hadronic collisions with entrained gas. Above and below become not just coordinates, but pathways for energy transport. The question lingers: how long does a galaxy remember an outburst after the visible fireworks fade? Fermi's all-sky monitoring revealed that the gamma-ray sky has both points and fog. Bright point sources include pulsars, blazars, and transient events that flare and fade. Diffuse emission fills broad regions and must be modelled to isolate the sources. The analysis becomes a battle between signal and the galaxy's own background glow. Each subtraction is a choice, and each choice can reveal or hide a structure. That diffuse glow is not a nuisance, it is a measurement of the halo's contents. Its spectrum can separate pion decay components from inverse Compton components, at least statistically. Spatial patterns can hint at where cosmic rays are densest, and where gas and photons provide targets. The high-latitude sky becomes a diagnostic of how far the galaxy's particle population extends. In effect, we're measuring an ecosystem. Particles, fields, photons, and the slow leakage of energy into space. This is the first correction to the night sky illusion in this chapter. Darkness at high latitude does not mean low energy, and it does not mean safety. Gamma rays can cross the galaxy with minimal deflection and minimal absorption by dust. If the flux changes, it can change quickly, and we might not see the cause in visible light. The warning is subtle because the sky can look unchanged while the radiation environment shifts, but gamma rays are not equally free everywhere, and distance introduces a filter. At extragalactic scales, very high-energy gamma rays can be attenuated by background light. A gamma ray can collide with an optical or infrared photon and produce an electron-positron pair. That process removes the gamma ray from the beam and sets a limit called the gamma ray horizon. It is a strange kind of opacity where light blocks light and the universe dims itself. The horizon depends on energy and on the density of the extragalactic background light. Lower energy gamma rays can travel farther, while the highest energies are absorbed over shorter cosmic distances. The universe becomes opaque to its own hardest photons, not because of dust, but because of light itself. Background starlight becomes a fog for gamma rays. When absorption happens, the energy does not vanish, but it is redistributed into particle cascades that re-radiate at lower energies. This matters for risk and for narrative tension. Some threats are local because only nearby sources can deliver the highest energy photons intact. Other signals are cosmically filtered, arriving only in softened forms after cascades. The gamma-ray horizon is a kind of safety curtain, but it is incomplete and energy-dependent. It does not protect us from our own galaxy. It also means that the most distant engines may be louder than they appear, their true power hidden behind the filter. So what could suddenly spike the gamma-ray flux at Earth? A nearby supernova could accelerate particles and brighten gamma emission over years, but the photons would not arrive as a single flash. A gamma-ray burst in our galaxy would be rarer, but it could deliver a short, intense dose. A magnetoflare could also produce a sharp high-energy transient, visible across the galaxy. Each scenario carries a different timescale, and that timescale determines whether we can respond or only endure. The dread comes from invisibility and speed, not from constant exposure. Gamma rays do not announce themselves to human senses, and they do not light up the sky. They arrive at light speed and pass through many materials, leaving damage only in chemistry and DNA. We learn about them only because detectors count what eyes cannot. It is an unsettling thought. The most violent light can be present, and the night still looks calm. Earth's atmosphere reduces the direct hazard, but it does not erase it. Extreme events can increase ionization in the upper atmosphere and alter ozone chemistry. Secondary particle showers can penetrate downward depending on energy and angle. Over geological time, rare spikes could leave subtle signatures in isotopes and extinction debates. The evidence, if it exists, would be indirect, written into chemistry, not into memory. Yet the same photons are also a tool because they point back to the galaxy's hidden engines. Gamma rays trace where cosmic rays are made, how they propagate, and where they interact. They can reveal pulsars behind dust and jets that would otherwise be missed. They can even constrain dark matter scenarios by limiting how bright annihilation could be. Limits matter in science because they narrow the space where speculation can hide. Bring the chapter back to above and below because geometry still matters. Looking out of the plane reduces confusion from dense gas and crowded sources. High latitude lets us isolate the halo's diffuse components and compare north and south. Any asymmetry can reflect our offset from the midplane or real structure in the halo. The symmetry we assume is often a convenience, not a fact. The solar system is not centered, and its small displacement changes the columns we look through. That changes the expected diffuse emission and the backgrounds we must subtract. It also means a source above the plane can be closer or less obscured than a similar source below. Above and below are not mirror images, even when the coordinate grid is symmetric. When we see differences, we have to ask whether they are physical or simply perspective. Gamma rays also connect to the gravitational story waiting in later chapters. Cosmic rays and hot gas respond to the galaxy's potential and to its magnetic scaffolding. The halo's particle population is shaped by escape, confinement, and winds that fight gravity. The high-energy sky is therefore a tracer of the same unseen mass that holds the system together. In a sense, gamma rays are a pressure gauge, hinting at forces that do not shine in visible light. So the chapter's logic tightens into a single claim. The emptiest-looking regions can host extreme accelerators and long-lived particle populations. Gamma rays arrive from above and below because the halo is active, not because the disk is quiet. The Milky Way is not only a band of stars, it is a volume filled with invisible traffic. The poles are not blank, they are simply written in a language our eyes cannot read. End with a forward pull, because this is a middle chapter and momentum matters. We have learned what gamma rays are, how they are made, and why the poles can shine. We have learned that distance adds a horizon that filters the hardest extragalactic signals. Now we ask what the gamma ray maps imply about the halo structure, and what hidden gravity is doing beneath that glow. The high-latitude gamma sky looks like background noise until you subtract it carefully, because the Milky Way itself glows in messy, overlapping layers. In 2010, analyses of Fermi's Large Area Telescope data revealed two vast lobes centered on the galactic center. They rose above and below the plane like mirror wounds, bright in hard gamma rays, and unnervingly clean once you knew where to look. At first, the signal hid inside the galaxy's own diffuse glow, which is produced by cosmic rays colliding with interstellar gas and by electrons scattering starlight. To expose anything new, researchers had to build detailed foreground models, then test them against the full sky. They adjusted gas maps, radiation fields, and cosmic ray distributions until the known emission could be peeled away. When the foreground was removed, a coherent structure remained, too large and too symmetric to ignore. The discovery was not just a matter of turning up contrast on a faint photograph. Gamma-ray astronomy works with sparse photons, and the sky is stitched together from years of detections, each tagged with energy and direction. The analysis depends on instrument response, background rejection, and careful statistics. A false structure can appear if the model is wrong by only a little, yet the bubbles persisted across methods and data cuts. That persistence is why the community stopped treating them as an artifact and started treating them as anatomy. The geometry was the shock, because geometry is hard to fake. Each lobe extends roughly 8 to 10 kiloparsecs from the galactic center, tens of thousands of light years tall. In silhouette, they look like two rounded pillars rooted in the nucleus, widening as they climb into the halo. Their edges are sharp, as if a boundary was drawn through the halo's fog and then held in place. Those edges matter visually and physically. On gamma-ray maps, the transition from bright bubble to dim background happens over a surprisingly small angle. In the language of plasma physics, that suggests a boundary layer rather than a gradual fade. If particles simply wandered outward at random, the border would blur with time. Instead, the bubbles look trimmed, like a pair of cavities with walls. The bubbles are not small features near the nucleus, and they are not subtle ripples in the disk. They occupy a significant fraction of the inner halo volume above and below the plane. From our offset position about 8 kiloparsecs from the center, we see them projected across a huge swath of sky. Even from inside the disk's clutter, they dominate the high-latitude gamma-ray view once you know their outline. Their spectrum deepened the mystery because it refused to behave like old, tired radiation. The emission is hard, meaning it stays strong at higher energies instead of fading quickly. In plain terms, the bubbles shine with energetic particles that have not yet cooled away. That hardness suggests recently accelerated particles, or a transport process that preserves energy while moving material far from the center. The edges are especially telling, because sharpness is a clock. A sharp edge implies confinement, a shock, or a rapid change in particle density across a thin region. Diffusion alone tends to smear boundaries over millions of years, unless magnetic structure limits cross-field motion. If the bubbles are old, something must keep their borders crisp. If they are young, something must have inflated them quickly. Soon the bubbles stopped being only a gamma-ray story, because other telescopes began to see echoes. X-ray maps showed large-scale arcs and limb-brightened features near the same region, hinting at hot plasma shaped by shocks. Microwave data revealed a diffuse haze toward the center, consistent with synchrotron emission from energetic electrons. The picture became layered, like a medical scan that shows bone, tissue, and blood flow in different colors. Multi-wavelength counterparts do not prove a single origin, but they constrain the physics in useful ways. Gamma rays can come from inverse Compton scattering by electrons, which boosts low-energy photons up to gamma energies. They can also come from pion decay after proton collisions, which is a hadronic pathway tied to gas density. X-rays trace hot gas and shocks, while microwaves trace electrons spiraling in magnetic fields. When these bands line up in the sky, they argue for shared structures even if the exact mechanism is debated. It helps to picture the environment the bubbles expand into. The galactic halo is not empty space, even if it looks dark in optical light. It contains tenuous plasma, magnetic fields, and a background sea of cosmic rays. It also contains the radiation fields that electrons can scatter, including the cosmic microwave background and the galaxy's own infrared and optical glow. The bubbles are therefore not just empty cavities, but regions where energy, particles, and fields have been rearranged. So the question becomes mechanical, not merely descriptive. What event in the galactic center could inflate two lobes so large, so symmetric, and so energetic? What could drive an outflow that remains coherent over kiloparsec scales, despite turbulence and the galaxy's rotation? If the bubbles are scars, what kind of wound leaves two matching marks on opposite sides of the disk? Candidate 1 is the black hole, Sagittarius A. Today it is quiet, accreting weakly and emitting modestly compared to active galaxies with blazing nuclei. Yet black holes are not defined by their current mood, because accretion can change dramatically when gas supply changes. The bubbles look like the after-image of a brighter phase, a mini-quasar episode in the recent past, when the center briefly behaved like an active galactic nucleus. In that scenario, accretion onto Sagittarius A launched jets, or a wide-angle wind that carried energy into the halo. The outflow punched into the surrounding medium, driving shocks and inflating cavities like a blowtorch carving into fog. Cosmic rays would be injected or accelerated, then trapped long enough to radiate. The bubbles become fossil lobes, the lingering glow of a short-lived engine. The nucleus can look calm now because the fuel is gone, not because the mechanism is impossible. Jets are attractive because they can deliver energy quickly and carve bipolar structures, which is exactly what we see in many radio galaxies. But the Fermi bubbles are broad, not narrow pencil beams, and their shape is more like two rounded chimneys than two needles. That pushes models toward either wide jets that later expand, or winds that begin wide and remain wide. It also raises a subtle question. Are we seeing the outflow itself, or the cavity it excavated? Candidate 2 is a nuclear starburst, because the inner few hundred parsecs can form stars in bursts. Massive stars live fast and die young, and their winds inject momentum long before their supernovae explode. When many such stars form in a compact region, their combined output creates overpressure. That overpressure can launch a galactic wind, a sustained flow that vents perpendicular to the disk where resistance is lowest. A starburst-driven wind naturally flows upward and downward because density drops fastest away from the plane. It can carry hot gas, magnetic fields, and cosmic rays into the halo, while entraining cooler material along the way. Over millions of years, it can inflate large lobes and enrich the halo with metals forged in stellar interiors. In visual terms, it is like a furnace that vents through two chimneys, leaving glowing walls where the flow meets the surrounding air. Candidate 3 is that both mechanisms operated together, which is not an exotic idea so much as a realistic one. A burst of star formation can feed the black hole by driving gas inward, while black hole feedback can compress or clear gas in the same region. The center may alternate between modes, leaving a blended signature in the halo. If that is true, the bubbles might record not a single event but a sequence of linked episodes. The symmetry could then be a time-averaged result rather than a single, perfectly balanced explosion. None of these origins is settled, and that uncertainty is part of the chapter's tension. The bubbles are real, but the trigger remains debated, and the debate is sharpened by how clean the structures look. The Milky Way shows us the scar, not the moment of injury. We are forced to reconstruct the event from residue, like detectives reading heat patterns after a fire. To understand the scar, we need the energy scale because size alone can mislead. Order of magnitude estimates place the total energy around 1055 to 1056 ergs, depending on composition and model assumptions. That is equivalent to tens of thousands of supernovae, or a brief period of black hole power sustained at a small fraction of its theoretical maximum. It is also enough energy to reshape the inner halo's pressure balance for a long time. Those numbers are not pulled from thin air, because they come from basic bookkeeping. You estimate the volume of the lobes, infer a pressure from the observed emission and plausible particle densities, and then compute the work required to inflate a cavity against its surroundings. The result depends on whether the interior is dominated by hot thermal plasma, by cosmic rays, or by magnetic fields. Each component stores energy differently, and each cools on different timescales. The bubbles therefore become a laboratory for the invisible energy budget of a galaxy. Timescales are similarly uncertain, and the uncertainty is not a weakness so much as a map of what we still do not know. Many models favour ages of a few million years, up to perhaps 10 million years. The sharp edges and hard spectrum often argue against very old ages, unless confinement is unusually strong. Yet the halo is difficult to measure directly, and small changes in assumed density or magnetic structure can move the clock. Age estimates come from several lines of reasoning that do not always agree. If the bubbles expand at hundreds to 1,000 kilometers per second, their size implies millions of years of growth. Cooling times for electrons also matter, because high-energy electrons lose energy through inverse Compton scattering and synchrotron radiation. If the electrons are too old, the spectrum should soften, especially at high latitude where the travel time is longest. The survival of sharp features adds another constraint, because edges erode unless something preserves them. But every estimate depends on assumptions about transport, and transport in a magnetized plasma is not intuitive. Cosmic rays do not move like smoke in still air, because their paths are guided and scattered by magnetic irregularities. They can advect with bulk flows, diffuse along magnetic turbulence, and sometimes stream along field lines at speeds regulated by plasma waves. A change in turbulence level can change the effective diffusion coefficient by orders of magnitude. That means the same observed shape can correspond to very different histories. Introduce the basic outflow physics, because the bubbles are essentially fluid dynamics drawn on a galactic canvas. A central energy injection drives a pressure gradient, accelerating gas and cosmic rays upward and downward away from the disk. A shock front can form where the outflow meets slower halo gas. heating plasma and compressing magnetic fields. Shocks are efficient particle accelerators, and they can also create thin shells where emission brightens. In images, those shells can appear as edges. Behind the shock, a cavity can fill with hot, low-density plasma, which is buoyant and resistant to mixing. Cosmic rays can be trapped by tangled fields, building pressure that helps support the bubble against collapse. The boundary can become a contact discontinuity, separating interior and exterior material without necessarily mixing them quickly. That boundary is where instabilities might grow, yet the observed smoothness suggests some stabilizing influence. Magnetic tension is a prime candidate for that stabilizing role. Advection matters when the bulk flow is fast, because it carries particles upward before they lose much energy. That naturally preserves a hard spectrum at high latitude, where the particles would otherwise have time to cool. Diffusion matters when turbulence scatters particles, spreading them and softening gradients. In reality, both processes operate together, and their balance can change with height. The bubbles force us to think about a coupled system rather than a single mechanism. Their sharp edges suggest limited cross-field diffusion, or a boundary where turbulence changes abruptly. Their large extent suggests sustained advection, or repeated injections that keep the lobes filled. If the interior flow slows with height, particles can accumulate and radiate, producing a relatively uniform brightness. If the flow remains fast, the emission might trace the edges where shocks and compression occur. The observed morphology therefore becomes a clue to the velocity field we cannot directly see. Magnetic fields are not a footnote in this picture, because they can shape the entire structure. As a cavity expands, field lines can drape around it, forming a sheath that suppresses mixing across the boundary. That sheath can also guide cosmic rays along the surface, enhancing edge brightness. Magnetic fields enable synchrotron emission, linking the microwave haze to the same electron population that may produce gamma rays. When we talk about a bubble, we're also talking about a magnetic container. Cosmic rays provide a second pressure component, and in some models they are the key driver. Cosmic ray pressure can help launch winds from the central region by adding an extra push beyond thermal gas pressure. As cosmic rays stream outward, they can excite alpha waves, which scatter the particles and transfer momentum to the gas. This coupling turns an invisible particle population into a mechanical agent. It is one of the ways a galaxy can move mass without relying solely on heat. The gamma rays then become a diagnostic of particle type, and that diagnostic is subtle. If electrons dominate, inverse Compton scattering on the cosmic microwave background and on starlight can produce the observed emission. The same electrons should also emit synchrotron radiation in microwaves if the magnetic field is strong enough. If protons dominate, collisions with gas produce pions that decay into gamma rays, and the protons can persist for long times because they cool slowly. The hadronic route therefore relaxes some timing constraints, but it demands enough target gas. Each channel predicts different side effects that observers can hunt for. Electron models predict strong microwave synchrotron with specific spectral slopes, and they can produce spatial correlations between microwaves and gamma rays. Hadronic models predict associated neutrinos, because charged pions decay into muons and neutrinos alongside the neutral pions that make gamma rays. They also imply a reservoir of gas in or near the bubbles, which is not easy to confirm. The halo is thin, and measuring its density is notoriously difficult from inside the disk. Observations offer hints but not a verdict, which is why the bubbles remain so compelling. The microwave haze supports energetic electrons and magnetic fields in the lobes, though its exact boundaries can be harder to define than the gamma edges. X-ray structures suggest shocks and hot plasma, but the halo's background makes interpretation difficult. Some X-ray features may be unrelated foreground structures, and some may be the bubble's skin. The challenge is separating a genuine limb from a coincidental overlap. Even the symmetry is not simple, and the details matter. The north and south bubbles are broadly similar, yet not identical in shape or brightness. Differences could reflect real asymmetry in the halo, such as density gradients or magnetic field variations. They could also reflect our viewing geometry from inside the disk, where dust and gas complicate the line of sight. When you're inside the system you are mapping, every feature is a projection. The bubbles look like two shapes on the sky, but they are volumes in 3 dimensions. The discovery also changed how we think about the Milky Way's centre, because it forced a re-evaluation of what quiet means. It is not only a region of old stars and dust-hidden orbits, and it is not only a gravitational hub, it is an engine capable of driving energy into the halo on galactic scales. That engine may idle for long periods, then flare when fuel arrives. The bubbles are evidence that the centre can couple to the halo, not just to the inner disk. This is another correction to the night sky illusion. Above and below are not passive directions into emptiness, even in our own galaxy. The halo can carry the memory of a central eruption long after the nucleus looks calm. In a dark sky panorama, the Milky Way's band seems like the whole story, yet the bubbles remind us that the most dramatic structures can be invisible to human eyes. What else is written in radiation we cannot see? The bubbles also connect to the Milky Way's long-term baryon cycle, which is the slow exchange of matter between disk and halo. Outflows can lift metals and heat into the circumgalactic medium, altering cooling and future accretion. If the centre erupted, it may have reshaped the halo's chemistry and pressure, changing how easily gas can fall back to form new stars. In that sense, the bubbles are not just scars but feedback, a mechanism by which the galaxy regulates itself. The question is whether the regulation is gentle, episodic, or occasionally violent. Active research now focuses on details that separate origins, because the broad outline is no longer in doubt. Are there clear shock signatures and X-rays at the edges, such as temperature jumps or compressed shells? Do polarization and Faraday rotation show magnetic draping, consistent with expansion, rather than unrelated foreground fields? Do spectral gradients reveal aging particles, or do they suggest fresh acceleration at specific locations? Each measurement is difficult, because the signals are faint and the foregrounds are bright. Some models propose in situ acceleration at the edges, which would make the boundaries not just walls but active sites. A shock can re-accelerate particles, keeping the spectrum hard near the boundary even if the interior is older. That would explain sharp edges without requiring perfect confinement over long times. It also creates a vivid image, a pair of enormous shock fronts, still energizing particles as they plow through the halo. If that is true, the bubbles are not merely relics. They are ongoing interactions between an ancient outflow and today's halo. Other models emphasize a central injection with rapid transport, where speed does the work that confinement would otherwise do. A fast wind can carry particles outward before they cool, then slow and fill the lobes as pressure equalizes. In that case, the bubbles are a record of direction and flow history, not only of total power. The edges could mark where the wind decelerates and piles up, rather than where it first breaks out. The distinction matters because it changes the inferred age and the required energy injection rate. Either way, the bubbles are a scale model of feedback seen in other galaxies, and that comparison adds weight to their significance. In starbursts and active nuclei, bipolar outflows are common, and they are often traced by radio lobes, X-ray winds, or optical emission line cones. The Fermi bubbles suggest the Milky Way has played that role, recently enough to leave a clear imprint. That is a humbling shift in perspective, because we often treat our galaxy as a calm baseline. The bubbles argue that calm may simply be a short phase between eruptions. Place the event in human perspective without claiming direct danger, because the timescales dwarf our stories. If the bubbles are a few million years old, the eruption happened long before recorded history, before agriculture, before cities. Yet on geological timescales it is recent, and it implies recurrence is possible. How often does the centre flare in this way, and what triggers the transition from quiet to outflow? If the answer is rare, the bubbles are a lucky catch. If the answer is cyclic, they are a warning about the galaxy's rhythm. The centre is quiet now, but quiet is not a guarantee, because the supply lines can change. Accretion can rise as gas is funneled inward by the galactic bar and by cloud collisions in the inner disk. Star formation can flare as conditions shift and feedback can follow, sometimes reinforcing itself. The same gravitational architecture that builds the nuclear region can also destabilize it. When enough mass piles up, the system can tip and energy can be released upward and downward. So Chapter 4 ends with a sharpened question, and the question points beyond these slow, giant lobes. If our galaxy can inflate twin stars tens of thousands of light years tall, it can also produce narrower, faster beams. Some beams are brief, lethal and unpredictable, and they do not need to be aimed at as often. The bubbles show that the Milky Way is capable of large-scale violence, even if it hides the evidence in wavelengths we rarely notice. Now the story pivots from slow, giant lobes to sudden flashes. If the Milky Way can erupt upward and downward, what catastrophic burst could strike from above without warning? The next chapter follows the most violent gamma events the universe can deliver. Now the story pivots from slow giant lobes to sudden flashes. The Fermi bubbles proved the Milky Way can vent energy upward and downward over long timescales, two vast chimneys glowing above the galactic centre. Gamma-ray bursts push that idea to an extreme because they arrive as brief, blinding spikes that vanish almost as soon as we notice them. A GRB is not a steady glow or a long flare, and it is not polite about timing. It is a transient burst of gamma rays, often followed by an afterglow at lower energies, as if the universe strikes a match and then lets the smoke drift. For seconds or minutes, it can outshine entire galaxies in gamma light, even when the source sits billions of light years away. In visuals, the prompt phase is a jagged heartbeat on a detector screen. Peaks stacked on peaks, separated by fractions of a second. Those spikes encode the engine's violence because gamma rays are produced where matter and magnetic fields are driven to extremes. The photons we catch are the survivors of a chaotic launch, compressed into a moment by relativistic motion. The first mystery was location, because early detectors saw bursts without clear direction. In the late Cold War era, instruments built to monitor nuclear tests began registering cosmic flashes instead, an accidental discovery that turned secrecy into astronomy. When better satellites triangulated positions, the sky distribution looked nearly uniform, with no preference for the Milky Way's bright band. That isotropy implied most bursts were far beyond the Milky Way, scattered across the cosmos. If GRBs were mainly local, they would cluster toward the disk where most stars live. Instead, they appeared like random pinpricks on a sphere, suggesting a deep, extragalactic origin. This is another correction to the night sky illusion. The empty-looking sky above and below the plane is not quieter, and it is not safer by default. It can host the universe's most violent flashes, arriving from any direction with no warning, silent to the eye, unmistakable to a gamma-ray detector. GRBs come in two main classes, separated first by duration. Long bursts last more than about 2 seconds, and many run tens of seconds, with complex multi-peaked light curves. Short bursts end in less than about 2 seconds, and some finish in a fraction of one, like a camera flash in deep space. Duration is not just a stopwatch category, because it tracks different engines and different environments. Long bursts are linked to the deaths of massive stars in star-forming regions, where gas clouds still glow and young clusters crowd together. Short bursts are linked to compact object mergers, often far from where the stars were born because time and gravity have had room to scatter them. Long GRBs are tied to core collapse, but not every collapse makes a burst, and that selectivity matters. The star must be massive, rapidly rotating and stripped of its outer layers, so the emerging jet is not smothered by a thick hydrogen envelope. When the core fails, a black hole or magnetar can form and drive a jet, converting gravitational energy into a narrow beam of radiation. In the collapsar or hypernova picture, the jet drills through the star like a blowtorch through fog. Deep inside, an accretion disk feeds the central object, and magnetic fields can wind into tight coils that fling energy outward. If the jet breaks out, gamma rays are produced in internal shocks or magnetic dissipation, where particles are accelerated and photons are boosted to high energies. If it fails to escape, the event may look like an unusual supernova without a burst, bright in optical light yet quiet in gamma rays. That hidden population is part of the beaming story too, because not every engine announces itself to every observer. The same physics can yield different skies, depending on whether the jet clears the stellar debris. Observations support this link through associations with type Ike supernovae. Several nearby long GRBs showed supernova light emerging days later, swelling beneath the fading afterglow like a second act. The spectra indicated stripped envelope explosions, consistent with the required progenitor, and the timing matched the idea that the burst comes first, then the expanding debris takes over. Short GRBs point to a different kind of catastrophe, one that begins with patience rather than sudden collapse. Two neutron stars spiral together, radiating gravitational waves as they lose orbital energy, and the orbit shrinks over millions or billions of years. When they merge, a brief jet can form and produce a short gamma flash, powered by a compact remnant and a transient disk. The smoking gun came when detectors caught both signals from one event. Gravitational waves marked a neutron star merger, and gamma rays arrived seconds later, delayed by the time it took the jet to form and the photons to escape. Optical and infrared follow-up revealed a kilonova powered by our process elements, forging gold, platinum, and other heavy nuclei in a radioactive glow. These two channels share a core idea. GRBs are not spherical explosions, and they are not isotropic beacons that shine equally in all directions. They are relativistic jets, narrow and fast, with Lorentz factors of tens to hundreds, meaning the outflow moves within a hair's breadth of light speed. Relativistic motion changes what we see, because beaming concentrates emission into a cone. The jet's radiation is Doppler boosted in the forward direction, and time itself seems compressed, because pulses are squeezed by motion toward the observer. To an aligned observer, the burst looks brighter, harder, and shorter, as if the universe is aiming a spotlight straight down the line of sight. Beaming is the chapter's central tension, because it turns geometry into fate. Most GRBs do not threaten Earth, because most jets point elsewhere, and the universe wastes no sympathy on our position. The danger comes from the rare alignment, not from the average event, and that distinction is where science replaces spectacle. A useful way to state it is the beaming fraction, which is simply the slice of sky illuminated by the jet. If a jet has an opening angle of a few degrees, only a tiny fraction of the sky lies inside the beam, like a laser pointer sweeping a stadium. That means the true GRB rate is much higher than the observed rate, because we only count the ones aimed at us. Risk estimates depend on that correction, and it cuts both ways. We see only the aligned bursts, so the universe is firing many more jets than we detect, and many galaxies host unseen catastrophes. But Earth is also a small target, so alignment remains unlikely, even in a cosmos that produces bursts frequently. The beaming fraction also changes energy accounting. The isotropic equivalent energy can be around 1052 to 1054 ergs in gamma rays, a number that sounds impossible because it assumes the burst shines everywhere at once. The true energy can be lower by orders of magnitude once the narrow cone is included, yet it remains among the most intense known explosions. Even with that correction, the engine is extreme, and the bookkeeping still stuns. A few solar masses of gravitational binding energy are available in collapse or merger, and the energy reservoir is real, not metaphorical. A small fraction channeled into a jet can still power a burst visible across billions of light years, crossing intergalactic space almost untouched. After the prompt gamma flash, many bursts leave afterglows, and those afterglows are where astronomy becomes detective work. As the jet plows into surrounding gas, it drives an external shock, heating and compressing the medium like a supersonic bow wave. That shock produces synchrotron emission from X-rays down to radio, fading over days to months as the blast wave decelerates. Afterglows matter for direction, because they reveal off-axis events that would otherwise slip past us. If we are outside the initial beam, the prompt gamma rays can be weak or absent, and the event may first appear as a faint rising glow. As the jet slows and spreads, the afterglow can brighten for off-axis observers, turning a missed shot into a delayed detection. This is why some bursts now look like structured jets rather than simple top-hat cones. Energy and Lorentz factor can vary with angle from the axis, with a fast core and slower wings that carry less power. That structure softens the boundary between safe and unsafe, but it does not remove it because the most damaging dose still comes from near-perfect alignment. Now, bring the story back to above and below the Milky Way. In earlier chapters, high latitude looked like a quieter direction, away from the crowded plain where dust lanes and star fields clutter the view. GRBs break that intuition, because extragalactic jets can arrive from any latitude, and the detector does not care where the constellations are. The galactic plane still matters for local sources. Massive stars form in the disk's spiral arms, where gas is dense and short-lived stars are common, and where stellar nurseries replenish the supply of potential collapses. Long GRBs would be more likely to originate near the plane if one occurred in our galaxy, simply because that is where the right kind of stars are born. But the poles are not protected by emptiness, and the word empty is itself a trick of human vision. A burst from another galaxy can come from high galactic latitude, because the source distribution is cosmic, not tied to our disk. Above and below become lines of sight, not safe zones, and the geometry of the jet matters more than the scenery. Direction also matters inside the Milky Way, because dust does not stop gamma rays. A jet aimed at us would deliver its prompt photons regardless of optical obscuration, punching through the same clouds that block starlight. The sky could look unchanged while chemistry in the upper atmosphere shifts, and the first warning might be nothing we can see. So what would a dangerous burst do to Earth? If it were close enough and aligned, and if its spectrum carried enough high-energy photons? The first interaction is atmospheric ionization, because gamma rays and hard X-rays deposit energy high above the surface, mostly in the stratosphere and mesosphere. They create cascades of secondary electrons that drive chemical reactions, turning air into a temporary plasma chemistry lab. One key pathway is nitrogen oxides, produced when energetic particles break molecular nitrogen and oxygen and allow new bonds to form. Those NOx compounds catalyze ozone destruction, meaning they participate in reactions that consume ozone while the NOx itself is regenerated. Ozone loss then increases ultraviolet B reaching the surface, stressing ecosystems that evolved under a steadier UV shield. In a visual sequence, the planet is shown as a blue sphere with a thin, glowing atmospheric shell. Then the shell thins, and ultraviolet light intensifies at the surface. The danger is not a single cinematic blast wave, but a slow biological pressure, measured in seasons and generations. What would it mean for plankton near the ocean surface, or for plants whose leaves cannot hide from the sun? This is the evidence-based core because the chemistry is testable and modelled. We understand ionization, catalytic cycles and UV impacts in broad terms, and we can compare them to known atmospheric perturbations. The uncertainty lies in event frequency, distance thresholds, and biological response details, because ecosystems are complicated and the past leaves incomplete records. The most common popular claim is a direct surface irradiation that sterilizes the ground. That is usually overstated because the atmosphere absorbs most prompt gamma energy, and the dose at sea level is typically not the main story. The larger hazard is indirect through ozone depletion and climate-relevant chemistry, with consequences that can persist long after the flash fades. There's also a second channel that can matter at very high energies. Air showers can produce muons that penetrate deeper than photons, reaching the ground and even the upper ocean with less attenuation. For typical GRB spectra, this is usually a smaller component than the chemical effects, but it reminds us that radiation is not a single thing. How close is close enough to matter, and how do we translate astrophysical energy into atmospheric damage? Models often cite distances of a few kiloparsecs for severe ozone depletion from a typical long GRB, which is a meaningful fraction of the Milky Way's disk. The exact number depends on jet energy, spectrum, and Earth's atmospheric state. Because oxygen levels and climate have changed over geological time, short GRBs can be dangerous too, even though they are briefer. Their spectra can be harder, pushing more photons into energies that ionize efficiently, and their jets can still carry immense energy. Their environments can be lower density, which affects afterglow brightness but not prompt hazard, because the prompt photons are produced within the jet itself. Now, separate speculation from evidence, because the documentary must hold that line. We do not have a confirmed GRB signature in Earth's geological record, the way we have iridium for an asteroid impact. We have hypotheses, plausibility arguments, and a few suggestive correlations that remain debated, because nature rarely labels its disasters. One often discussed idea links a nearby GRB to the late Ordovician extinction. The timing could fit a sudden ozone shock and selective damage to surface and shallow water life, especially in organisms sensitive to UVB, but the evidence is circumstantial, and alternative causes are strong, including glaciation, sea level change, and complex ecological cascades. Another proposed clue is unusual nitrate spikes or isotope anomalies in ice cores, which would be a chemical echo of atmospheric ionization. Such signals can also be produced by solar proton events and other atmospheric disturbances, and the atmosphere mixes and erases patterns over time. Without a unique fingerprint, attribution remains uncertain, and uncertainty is not a weakness but an honest boundary. So the responsible claim is narrower, and it is still unsettling. A sufficiently close aligned GRB could damage the ozone layer and raise UV exposure for years, with ecological stress that depends on latitude, season, and food web resilience. Whether that has happened in the last few 100 million years is not settled, and the silence of the record is not proof of safety. The risk question then becomes statistical rather than cinematic, and statistics demand context. GRBs are rare in any one galaxy, and rarer still in metal-rich environments like the modern Milky Way, where stellar winds strip angular momentum and make collapses less likely. Long GRBs prefer low metallicity massive stars, which were more common earlier in cosmic history, when the universe had fewer heavy elements. That metallicity bias is a partial safety factor, not a shield, and it comes with a caveat. It suggests the Milky Way today is less likely to produce a long GRB than some smaller, metal-poor galaxies, where massive stars can retain rapid rotation. It does not eliminate the possibility of an unusual progenitor, or a rare evolutionary pathway that keeps the core spinning. Short GRBs do not require massive star formation, so they do not track the disk as tightly. Neutron star binaries can merge long after they form, and kicks can move them far from the plane, because supernova explosions are not perfectly symmetric. A short GRB could occur in the halo, or even outside the disk, and still aim inward by chance. That complicates the above and below geometry again. A local merger could happen at high latitude because the binary wandered there, and the surrounding sky could look almost empty in visible light. The jet could then point toward the solar system from a direction that looks empty in starlight, turning quiet into exposed in a single alignment. Now widen the frame to the extragalactic shooting gallery. The universe contains billions of galaxies, and GRBs occur somewhere in that volume every day, a steady drumbeat of distant catastrophes. Most are too distant to matter physically, but they define the background probability of alignment, and they remind us that the sky is active even when it appears still. Distance is a filter, but not the one we used for steady gamma rays. For GRBs, the prompt emission is typically in the keV to MeV range, which travels across the universe with little attenuation by dust or gas. The gamma ray horizon mainly limits the highest energy components, where interactions with background light can absorb photons over cosmological distances. So the dangerous part for Earth is not blocked by intergalactic light, and it does not fade into harmlessness because of dust. If a nearby galaxy produced an aligned burst, the photons would arrive essentially unsoftened, carrying their ionizing power intact. The limiting factor is proximity, not transparency, and proximity is a matter of local cosmic geography. Place the solar system on a map of local space, and the scale becomes personal. Nearby star-forming regions in the Milky Way's disk are closer than most external galaxies, and some lie within the few kiloparsec range that models flag as consequential. That makes the disk the main arena for a truly close-long GRB, even if the probability is low and the required progenitor is rare. But the poles still matter for perception and for detection. High galactic latitude has less diffuse gamma background, so bursts are easier to localize against the sky, and follow-up telescopes can identify afterglows with less confusion. The same emptiness that fools our eyes can sharpen our instruments, because fewer foreground sources clutter the search. This connects back to the earlier problem of confusing backgrounds and unidentified sources. GRBs are not part of the persistent unidentified population, because they are transient and unmistakable in time, and their light curves act like signatures. Yet their afterglows can be faint, and host identification can be difficult, especially when the burst occurs in a dim galaxy or far from its center. It also connects to the dark matter hypothesis by contrast. Dark matter signals would be steady or slowly varying, spread across the halo, and hard to separate from astrophysical fog that mimics the same energies. GRBs are the opposite, a clean spike that proves nature can do violence without ambiguity, then leaves us to interpret the quieter aftermath. Now return to beaming as the narrative spine, because it is the mechanism that turns cosmic power into selective danger. A burst aimed away is an event we never see, and it is harmless to us no matter how energetic it was at the source. A burst aimed toward us is a brief alignment of jet axis and planetary atmosphere, turning random geometry into consequence. We can express that consequence in simple probability language, even if the numbers remain uncertain. For a jet opening angle of 5 degrees, the beaming fraction is roughly 1 in a few hundred, because the illuminated patch on the sky is small. That means for every GRB we see, hundreds more occur unseen, and our catalogues are only the tip of a much larger rate. But Earth's risk is not the same as the cosmic rate, and that distinction is where fear can be disciplined. Only bursts within a few kiloparsecs matter strongly, and those are rare, especially for long GRBs in a metal-rich disk. The product of rarity and alignment yields a low probability, but not a zero probability, and the difference between low and zero is where unease lives. The chapter should not end in panic because the science does not justify it, and the timescales are not human. It should end in unease because the mechanism is real, and the alignment is out of our control, and the sky does not negotiate. Above and below are not moral directions, only angles in a firing range, quiet to our senses, active in physics. Now tighten the link to the central question. What is truly above and below the Milky Way from our solar system's point of view, when the most important variable is not scenery but trajectory? In the GRB story, above and below are not places, they are trajectories that can intersect us. An intersection is what turns astronomy into hazard. The sky's symmetry is a trap because danger does not respect the plane. A jet can arrive from the disk, from the halo, or from a distant galaxy projected over the poles, and the detector would register the same kind of spike. The difference is not brightness to our eyes, but geometry and distance, and the question of whether the beam happens to include one small planet. End with a forward pull, because radiation is only half the story. Gamma rays arrive as sudden messages, but gravity is the slow current that sets where we travel and what neighbourhoods we pass through, shaping long-term exposure without drama. Beneath the visible sky, the galaxy's mass is steering our future encounters, quietly shifting our position in the cosmic shooting gallery. Next, we follow that hidden pull because it shapes the odds of what can strike from above or below. The shooting gallery is not static, and our path through it is written by gravity we cannot see, traced in orbits that unfold over millions of years. End with a forward pull because radiation is only half the story, and it is the faster half. Gamma rays arrive as sudden messages, sharp as a camera flash, but gravity is the slow current that sets our route. The sky looks symmetric from Earth, yet our solar system is not centered, not still, and not drifting freely. This chapter pivots from photons to force. We move from what strikes us to what steers us, from bursts of energy to the quiet geometry of motion. Below becomes a metaphor for the unseen scaffolding that guides trajectories, even when the sky looks calm and perfectly balanced. Start with the Milky Way as a gravitational potential, not a picture on a planetarium dome. In physics, a potential is a landscape of energy, valleys and slopes that dictate how objects accelerate. The disk, the bulge, and the halo each contribute to the pull we feel, and their combined field sets the rules for every orbit. Visually, imagine the galaxy not as a glowing spiral, but as a contour map drawn in darkness. Where the contours bunch together, gravity is steep and motion tightens. Where they spread out, the pull is gentler, and orbits can widen without breaking. The disk is thin in height but heavy in influence near the plane, like a dense sheet hidden inside the starlight. Most stars and much of the gas live there, concentrated into a flattened mass layer shaped by rotation. Close to the mid-plane, the disk's gravity dominates vertical motion and creates a restoring force that points back toward the center line. That restoring force is not a metaphor, and it is not a guess. Near the plane, gravity behaves almost like a spring, because the mass is distributed in a slab. Move a little above the mid-plane, and the pull back downward grows roughly in proportion to height, at least for small displacements. On screen, the disk can be shown edge-on as a razor-thin band, bright at the center and fading outward. Dust lanes cut through it like smoke, and star-forming regions glitter in scattered knots. Beneath that beauty sits the disk's mass, quiet, persistent, and mechanically decisive. The bulge adds a central weight, dense and compact compared to the disk's broad spread. Its gravity matters most in the inner galaxy, where orbits tighten and speeds rise, and where stars crowd into a thicker, older population. Even from far out, the bulge contributes to the overall depth of the potential well, like a heavy stone placed at the center of a stretched fabric. Historically, astronomers first argued over the Milky Way's structure using star counts and dust-corrected maps, long before they could measure precise galactic motions. The bulge was once a hazy inference, a swelling in the star distribution toward Sagittarius. Today it is a measured component, tied to kinematics and to the galaxy's central dynamics. The halo is different because it is extended and mostly invisible, and its influence grows as the light thins. Its mass is spread over a huge volume, reaching far beyond the bright disk and beyond the outermost spiral arms. At large radii, the halo's gravity becomes the main reason the outer galaxy stays bound, even where the sky seems nearly empty. If the disk is the luminous surface, the halo is the depth beneath it, an unseen reservoir shaping the whole. You can picture it as a vast diffuse sphere surrounding the galaxy, with a density that declines slowly with distance. The farther you go, the more the halo dominates what the galaxy can hold on to. We can test this layered gravity without leaving the galaxy, because motion carries the signature of mass. We measure how fast gas and stars orbit at different distances from the centre, using Doppler shifts in spectral lines. Those measurements form a rotation curve, a plot that turns motion into a map of mass. The method is conceptually simple, even if the observations are demanding. If you know an object's orbital speed and its radius, you can infer how much mass lies inside that orbit. In plain terms, fast motion at large distance implies strong gravity, and strong gravity implies a lot of mass. Early in the 20th century, astronomers began to realize that galaxies were not just collections of stars, but dynamical systems. Later, as radio astronomy matured, neutral hydrogen became a crucial tracer. Hydrogen's 21 centimeter line can be measured far beyond the bright stellar disk, extending the rotation curve into the dark outskirts. If visible matter were most of the mass, orbital speed should drop with distance once you pass the bright regions. Outside the luminous disk, gravity would weaken like a fading spotlight, and the curve would fall. The rotation curve should decline, roughly like planets slow down far from the Sun, where the Sun's mass dominates and little else contributes. That expectation is not arbitrary, because it follows from Newtonian gravity in a system where most mass is centralized. When mass stops accumulating with radius, the gravitational pull drops as distance increases. In such a case, orbital speed should decrease, and the outskirts should move more slowly. But the Milky Way does not behave that way, and neither do many of its spiral cousins. Speeds stay high far beyond where most starlight lives, even where the disk becomes a faint haze. The rotation curve stays flatter than expected, which means the enclosed mass keeps rising with radius long after the light has tapered off. This is another correction to the night sky illusion. The galaxy's light is not the galaxy's weight, and brightness is not a reliable proxy for mass. The parts we see cannot provide enough gravity to hold the observed speeds, at least not with ordinary matter alone. Introduce the dark matter halo as the simplest explanation that fits the data and preserves the logic of gravity. Dark matter is inferred from gravity, not detected through emitted light, and that distinction matters. It acts like mass, it clusters like mass, and it shapes orbits without shining, as if the galaxy were embedded in an invisible scaffold. The phrase dark matter can sound like a poetic label, but it is a technical placeholder for a real gravitational requirement. Something must supply the missing pull, and it must do so on galactic scales. The halo is not a decorative add-on, it is what makes the observed motions dynamically coherent. Clarify what dark matter is not, because confusion is common, and the alternatives have been tested hard. It is not ordinary dust hiding in the dark, because dust would absorb starlight and re-radiate energy in infrared. If dust were that abundant, the galaxy would glow differently, and the energy budget would not balance. It is not a vast population of faint stars at the required level, because surveys constrain that strongly. If the halo were packed with dim red dwarfs or dead stellar remnants, we would see their gravitational microlensing effects more often. We would also detect their cumulative light and their chemical fingerprints, and the numbers do not match. It is also not just gas we forgot to count, because gas leaves spectral fingerprints across the electromagnetic spectrum. Hydrogen glows in radio, ionized gas glows in emission lines, and hot gas glows in X-rays. The missing mass is missing across wavelengths, yet present in dynamics, which is why the problem refuses to disappear. Connect back to earlier chapters, where gamma maps hinted at a halo beyond starlight and tempted us with indirect signals. High-latitude emission can trace cosmic rays, outflows, and diffuse backgrounds that complicate interpretation. Gravity provides a second independent probe of the same hidden structure, and it does not depend on how particles radiate. In a documentary frame, the contrast can be shown as two overlays on the same galaxy. One layer is the luminous disk, textured with star clouds and dust lanes. The other is an invisible mass map, smooth and extended, revealed only by the way everything moves. Now narrow the scale from the whole galaxy to our own orbit, because the invisible river runs through our neighborhood too. The Sun circles the galactic center at roughly 8 kiloparsecs, a distance so large it turns our familiar sky into a local bubble. That orbit is not a perfect ring, because the disk is structured and the potential is not perfectly smooth. The Milky Way is not a rigid wheel, and its mass is not evenly distributed. Spiral arms, giant molecular clouds, and subtle asymmetries add small perturbations to the gravitational field. Over time, those irregularities can nudge orbits, changing them slightly without breaking the overall bound motion. We also move up and down through the galactic mid-plane, a motion that is easy to miss because it is slow. The Sun oscillates vertically, crossing the plane and rising to one side, then returning. The timescale is tens of millions of years, order of magnitude around 50 to 100 million, which is long for a human story but short for a galaxy. Explain the mechanism in simple terms while keeping the physics intact. The disk's gravity pulls toward the midplane like a restoring spring, because the mass is concentrated in a flattened layer. When the Sun is above the plane, gravity accelerates it downward, and it overshoots through the middle, continuing until the pull reverses. The oscillation is not a dramatic plunge, and it is not a straight line through space. It is a gentle bobbing superimposed on our broader motion around the center, like a slow swell beneath a steady current. Over geological time, the solar system samples different heights in the disk's gravitational field, and that sampling subtly changes what surrounds us. A visual sequence can make this tangible, because the motion is otherwise abstract. Show the Milky Way edge on, with a thin luminous band and a faint halo glow. Then trace a small marker, our Sun, rising above the band, crossing through it, and drifting below, all while continuing forward around the center. Tie above and below to this motion, because the metaphor now becomes physical and measurable. Above and below are not permanent addresses, they are faces of an orbit shaped by a mass distribution. Our position relative to the plane changes slowly, regardless of what the night sky suggests, and regardless of how fixed the constellations appear. Mention why this matters without overclaiming, because the environment does vary with height. The density of gas, dust and stars is higher near the plane, and the midplane hosts many energetic processes. Crossing the midplane can change the environment, from radiation fields to encounter rates with clouds and remnants, even if the changes are modest. Near the plane, the interstellar medium is thicker, and the probability of passing near dense molecular clouds increases. Those clouds are the cradles of star formation, and they also carry magnetic fields and turbulence. Farther from the plane, the medium thins, and the sky becomes more dominated by diffuse high-latitude structures. Keep the boundary between evidence and speculation clear, because it is tempting to turn cycles into prophecies. Some have proposed links between plane crossings and impacts or extinctions, often by searching for periodicity in crater records. The timing is uncertain, the mechanisms are debated, and correlation does not equal cause, especially when geological data are incomplete. Still, the question lingers in the background as a disciplined curiosity rather than a claim. If the galaxy has layers of density and activity, what subtle changes might a vertical oscillation impose over deep time? And how many apparent patterns vanish once uncertainties are treated honestly? Now widen back to the galaxy and return to the rotation curve as a central clue, because it is the cleanest bridge from local motion to global mass. Flat curves are not unique to the Milky Way. They appear in many spiral galaxies across different sizes and brightnesses. The pattern suggests a common component that extends beyond the luminous disk, and it appears with a stubborn consistency. That component behaves like a halo that grows in importance with radius, becoming the dominant term where starlight fades. It deepens the potential well and keeps outer orbits fast, even where the visible mass is sparse. Without it, many galaxies would be dynamically inconsistent with what we observe, and some would not remain stable over cosmic time. In narration, this is where the invisible river metaphor earns its weight. The luminous disk is the surface shimmer, where we can see ripples and bright eddies. The halo is the deeper channel, the hidden volume that carries the flow and sets the speed. Connect this to the documentary's earlier dark matter thread, because the audience has already seen how tempting indirect light can be. Gamma rays offered a way to see dark matter indirectly, through annihilation or decay signals that might produce faint characteristic glows. But backgrounds from pulsars, remnants, and diffuse emission can mimic faint glows, and the sky rarely labels its sources. Gravity is the cleaner baseline because it does not care about emission mechanisms or astrophysical clutter. It measures mass through motion, even when the mass is dark, and it works in every direction we can observe. Yet gravity alone cannot tell us the particle identity, only the distribution and the total amount required. That limitation is part of the mystery, and it sharpens the tone rather than weakening it. We can weigh the unseen with exquisite confidence and still not know what it is made of. The universe allows the measurement, but withholds the ingredient list. Now introduce gravity as a current, because we are not only orbiting the Milky Way, and the river has tributaries. The solar system has a peculiar velocity, a motion relative to the cosmic microwave background. The CMB provides a rest frame defined by its dipole anisotropy, and it gives the cosmos a subtle directional cue. We see the CMB slightly hotter in one direction and cooler in the opposite, a temperature difference spread across the whole sky. That dipole indicates our motion through the universe on large scales, like a wind you cannot feel but can measure. It is a reminder that we are carried by flows larger than any single galaxy, and that still is often just slow. Explain what peculiar velocity means in this context, because the phrase can sound technical without grounding. It is the difference between our actual motion and the smooth expansion of the universe, the motion left over after subtracting the Hubble flow. It reflects gravitational attraction toward mass concentrations and away from underdense regions, as matter responds to the cosmic landscape. The local group is moving together, not as isolated islands scattered in a void. The Milky Way and Andromeda share a bound system, with smaller galaxies orbiting in a common gravitational field. Their mutual pull is local, but the drift of the group is larger, layered on top of the internal dance. Name the idea without turning it into a catalogue of structures, because the point is the principle. Large-scale gravity tugs us toward overdensities in the cosmic web, and those overdensities are not always obvious in visible light. The web is built from filaments of matter and nodes of clusters, mostly dark in composition, and it organizes where galaxies form and how they move. Make the metaphor explicit and disciplined, so it stays scientific rather than decorative. The gravitational field is the riverbed, and our galaxies are carried like boats that respond to the slope. We do not feel the flow as a wind, we infer it from velocities and from the CMB's dipole, and from the way groups of galaxies stream together. This is another correction to the night sky illusion, and it is one of the most unsettling. The universe is not a static dome of lights, pinned in place above a quiet Earth. It is a moving network of mass, and our position changes even when constellations look fixed, because the changes are measured in millions of years. Link back to the chapter title and to Beneath the Plane, because the phrase now carries multiple scales. Beneath the bright band lies the dominant mass budget, spread through a halo we cannot see. The disk is the luminous surface, but the halo is the deep channel guiding motion, and beyond that channel lie larger currents in the cosmic web. Reinforce the layered gravity concept with one clean recap, now enriched by the journey we have taken. The disk shapes vertical oscillations and local restoring forces, tightening motion toward the midplane. The bulge deepens the central well and influences inner orbits, where speeds rise and paths crowd. The halo maintains high speeds and binds the outer galaxy, extending the system's reach far past its light. Now connect the halo to the larger cosmic web, because halos do not form alone and they do not end at the edge of a photograph. Dark matter collapses first, creating wells that baryons fall into later, and those baryons become the stars and gas we can see. Galaxies grow inside those wells, and their halos link into filaments on larger scales, as if individual eddies were embedded in a continental current. Historical context deepens the sense of continuity, because this is not a new question with a new name. For decades, astronomers have compared what they can see to what they can weigh, and the mismatch keeps returning. Each new survey refines the map, but the central lesson remains: most of the mass is not luminous. Keep the mystery tone without adding new claims, because the power here is in restraint. We can map the river by watching how objects move, even when we cannot see the banks. Every orbit is a measurement, and every speed is a clue, and the clues agree across scales that should not easily agree. Now set up the next chapter with a clear outward zoom, because the current does not stop at the Milky Way's edge. To understand what is pulling us, we must zoom out beyond the Milky Way, past the local group, into the architecture of the universe. The next scale of above and below is written in the cosmic web, where filaments and voids define the long slopes of gravity, close by tying force back to hazard and trajectory, because the documentary's tension depends on both. Radiation is a sudden threat, but gravity decides which neighbourhoods we pass through and which encounters become possible. The invisible river does not announce itself, yet it carries us toward whatever comes next, and it does so with patient, relentless precision. End with a forward pull, because gravity does not stop at the Milky Way's edge, and it does not respect our maps. Chapter 6 weighed our halo and mapped a hidden river inside the galaxy, using motion as a proxy for mass. Now we follow that river outward, past satellite galaxies and tenuous gas, into intergalactic darkness, and ask what it flows toward. The first clue is not a galaxy, but a background glow behind everything. Faint, ancient, and almost perfectly smooth. The cosmic microwave background is relic radiation from the early universe, released when the first atoms formed and light finally travelled freely. That moment, called recombination, happened when the universe cooled enough for electrons to bind to nuclei, and photons stopped scattering like headlights in fog. Over time, as space expanded, that light was stretched into microwaves, cooling into a uniform bath that still fills the sky. Its spectrum is an almost perfect black-body curve, a thermal fingerprint that tells us the early universe was once hot, dense, and in near equilibrium. Even the uniform part is a measurement with astonishing precision, because the CMB varies by only tiny fractions across the whole dome. Visually, the CMB is a sphere around us, like a shell of afterglow painted on the inside of the universe. When instruments translate microwaves into colour, the map looks like mottled static, but the mottling is meaningful. It encodes tiny temperature differences, the fossil imprint of early density variations that later grew into galaxies and clusters. Those speckles are not noise in the casual sense, and they are not artistic texture added for drama. They're acoustic scars from pressure waves in the primordial plasma, frozen at the instant light decoupled from matter. In plain language, the early universe rang like a bell, and the CMB preserves the pattern of that ringing. The CMB acts like a universal rest frame, not because space has a preferred centre, but because this radiation fills space almost evenly. If we were perfectly at rest with respect to it, the CMB would look the same in every direction, down to the limits of our detectors. Instead, it shows a dipole pattern, hotter in one direction and cooler in the opposite, as if the whole sky were gently tilted. That dipole is a Doppler effect on a cosmic scale, produced by our motion through the CMB bath. The physics is familiar in plain language. Moving toward a wavefront compresses it, while moving away stretches it. In the CMB, that compression means a slightly higher measured temperature ahead of us, and a slightly lower one behind. The amplitude encodes a speed, but the key idea is directional, and direction is what this chapter needs. The sky itself points, and it points consistently across instruments, calibrations, and decades of analysis. When different satellites agree on the same dipole axis, the result stops feeling like a measurement and starts feeling like a compass. On screen, the dipole can be shown as a subtle gradient across the entire celestial sphere, with one hemisphere warmed by motion and the other cooled by retreat. It is a gentle effect, yet it dominates the CMB map once the smaller speckles are set aside. The universe, in a sense, gives us a built-in arrow, one that ignores our constellations and cuts through our myths. This is another correction to the night sky illusion. The constellations look fixed, yet the whole local group is moving through space, and it is moving in a specific direction. Above and below are not symmetric when one hemisphere is slightly blue shifted by our drift, and the other is slightly red shifted in retreat. Now bring the story back to above and below the Milky Way, because direction is the chapter's engine, and the camera needs a heading. The CMB dipole gives us that heading, like a compass that works beyond stars and beyond the Milky Way's bright band. It tells us our peculiar velocity, the motion left after subtracting smooth cosmic expansion and the average Hubble flow. Peculiar velocity is gravity made visible through kinematics, and it is one of the cleanest ideas in observational cosmology. Matter is not only carried outward by expansion, it also falls inward toward overdensities, because gravity builds gradients in the cosmic potential. The result is a flow field, where galaxies stream along the slopes of the cosmic web, even while the background universe expands. To understand the tug, we need the web itself, built from tiny early fluctuations that were once measured as mere parts per 100,000. In the early universe, density variations were small, but gravity amplifies them over time, and it does so relentlessly. Slightly denser regions pull in more matter, growing faster, while underdense regions lose matter and become emptier relative to the mean. Over billions of years, this instability sculpts filaments, walls, and voids, and the shapes are not artistic metaphors. They are dynamical outcomes. Filaments are elongated bridges of dark matter and gas where galaxies form, align, and often spin in correlated directions. Walls are broader sheets that bound large empty regions, while voids are underdense basins that redirect flows outward, like valleys that have been drained. In simulations, those filaments glow in false colour, as if the universe had veins, and the brightest knots mark where gravity has had the longest time to work. In real surveys, the same pattern appears more quietly, as chains of galaxies and clusters stitched across hundreds of millions of light-years. The match between simulation and observation is one reason cosmologists trust the web as more than a metaphor. Voids are not truly empty, and that detail matters for the narrator's tone. They contain thin gas, faint dwarf galaxies, and dark matter at lower density, but their defining feature is contrast. A void's gravity is weaker than its surroundings, so matter tends to stream away from it, making the edges denser and the interior quieter. The cosmic web is not decoration. It is the large-scale gravitational landscape, and landscapes create paths. Galaxies do not move randomly through it. They drift along it like leaves in a slow current, responding to a field they cannot see. Clusters sit at nodes where filaments intersect, and those nodes become deep wells in the map, places where trajectories converge. Now widen the scale again, because our motion is not explained by one nearby neighbour, and the CMB dipole demands a broader accounting. The local group's internal dynamics include the Milky Way and Andromeda falling together, a future collision written into their mutual gravity. Yet the dipole implies an additional drift shared by many nearby galaxies, as if our whole neighbourhood were being carried downstream. Astronomers began to map that drift by measuring galaxy distances and velocities, turning the sky into a dataset rather than a panorama. Redshift gives recession speed through the stretching of spectral lines, but distance is harder and requires standard candles and scaling relations. When you compare redshift with distance, you can separate Hubble expansion from local departures, and those departures are where gravity leaves fingerprints. Distance indicators come with uncertainty, and that uncertainty becomes part of the story. Cepheid variables pulse with a period that reveals their intrinsic brightness, while Type Ia supernovae act as bright, calibratable beacons across large volumes. Spiral galaxies follow the Tully-Fisher relation, where rotation speed correlates with luminosity, and ellipticals follow the fundamental plane, linking size, brightness, and velocity dispersion. Each rung of this distance ladder must be cross-calibrated, because a small systematic error can tilt an entire flow map. Astronomers argue over dust corrections, metallicity effects, selection bias, and the subtle ways galaxies refuse to be perfectly standard. The result is not weakness, but transparency. Uncertainty is tracked, propagated, and used to test how robust the inferred tug really is. When these methods are combined, the map gains depth, and the flow becomes visible as a pattern rather than a rumour. Those departures reveal coherent streaming motions, not isolated quirks or measurement noise. Groups and clusters in our region tend to move in similar directions, suggesting a large mass concentration pulling on a vast volume of space. Historically, this is where the phrase Great Attractor entered the story, and it entered with the drama of a missing object. In the late 20th century, as peculiar velocity catalogues improved, the numbers implied a convergence that seemed too organised to ignore. It was a name for an inferred region of excess gravity, not a single confirmed body with a clean outline. The idea was simple and unsettling, because it implied a hidden basin influencing our trajectory, and it implied we were not seeing the full cause. If galaxies were streaming, then something massive was shaping the slope of spacetime in our neighbourhood. The question was whether that something was one dominant structure, or a crowded landscape blurred into one label. The mystery sharpened because the suspected direction lies near the Milky Way's plane, right where our own galaxy becomes an obstacle. Our galaxy blocks the view with dust lanes, gas clouds, and dense star fields that flood detectors with foreground light. This is the zone of avoidance where optical surveys lose galaxies behind foreground clutter, and where the universe seems to stop simply because our eyes cannot continue. The zone of avoidance is not a true absence of galaxies, it is an observational blind spot, and the distinction is crucial. Dust absorbs and reddens starlight, shifting colours and dimming distant systems until they fall below detection thresholds. Crowded stellar fields confuse source identification, and even when galaxies are present, their shapes and brightness are distorted by extinction and confusion. On screen, the Milky Way's band becomes a bright scar across an all-sky map, and that scar is not just beautiful, it is a mask, a reminder that our vantage point is embedded inside the very object we use as a reference. The Great Attractor direction sits behind that mask, so the story naturally becomes one of inference under constraint. This is another correction to the night sky illusion. The Milky Way's bright band is not just scenery, it is a barrier to certain kinds of knowledge. It hides parts of the external universe, including the very direction our motion seems to point, and it forces astronomers to become translators between wavelengths. Now, separate speculation from evidence, because the documentary must hold that line and keep the mystery honest. The Great Attractor was never a claim of one monster object with a clear edge, like a cosmic vacuum cleaner. It was a hypothesis built from velocity fields, incomplete sky coverage, and the assumption that mass traces light, at least approximately. Early reconstructions use sparse data and strong smoothing, which can create apparent centers even when the underlying structure is complex. If you average too much, a landscape of ridges and basins can look like one peak, and the math will happily supply a center. The label Great Attractor captured the drama, but it also risked oversimplifying the physics, turning a gradient into a villain. There is also a deeper caution here, and it echoes the scientific method itself. A flow field is not a photograph, it is a reconstruction, and reconstructions inherit the biases of their inputs. When distances are uncertain and the sky is partially missing, the safest conclusion is not a single object, but a range of plausible mass distributions. The way forward was to see through the mask using other wavelengths, because dust is selective in what it blocks. Infrared surveys can penetrate dust better than visible light, revealing galaxies dimmed in optical bands and restoring continuity to the map. Radio surveys can bypass dust almost entirely, especially using the 21 centimeter line of neutral hydrogen, which travels through the plane with little attenuation. The 21 centimeter HI line is a powerful tool because it traces gas-rich galaxies even when starlight is hidden behind the Milky Way's glare. It also provides a redshift directly from the radio spectrum, turning detection into kinematics in one step. With wide-area HI surveys, astronomers began filling in the missing sky behind the plane, pixel by pixel, galaxy by galaxy. As coverage improved, the hidden region stopped looking empty and started looking structured, like a coastline emerging from fog. Clusters and superclusters emerged where the Milky Way once seemed to erase the universe, and the map gained texture behind the bright band. The Great Attractor direction contained real concentrations, but not a single obvious culprit with a unique signature. Now the detective story becomes a map-making story, and map-making is where modern cosmology earns its confidence. We combine distance indicators, redshifts, and sky surveys across wavelengths, then cross-check them against one another. We reconstruct a three-dimensional flow field, then ask what mass distribution best explains it, using gravity as the governing rule. One conceptual step matters here, because it connects directly to Chapter 6's halo logic, and keeps the narrative coherent. Gravity is inferred from motion, not from brightness alone, and motion does not care whether matter shines. Dark matter can dominate the mass budget, so the deepest pull may not coincide with the brightest light, and the brightest light may sit on a slope. This echoes the earlier gamma ray thread about confusing backgrounds and false positives, where the sky can mislead without context. In gamma rays, diffuse emission can mimic a new signal, and the sky rarely labels its sources for us. In large-scale structure, incomplete sampling can mimic a single attractor, and the map rarely labels its missing regions, so interpretation becomes part of the craft. The modern picture replaces the single attractor myth with a basin of attraction framework, which sounds abstract until you visualize it as topography. Our local region is part of a larger supercluster scale flow called Laniakea, a name that suggests an ocean because it behaves like one. Laniakea is defined by the way galaxies move, converging toward a gravitational basin rather than a sharp boundary drawn on a chart. In this view, the Milky Way is one boat in a fleet, all drifting toward the same low point in the potential, and the fleet is enormous. The basin is not a point mass. It is a region where many filaments and clusters contribute, each adding a small piece to the overall slope. The Great Attractor becomes a name for the local gradient of that basin, not a single hidden monster. Yet the story does not end there, because the flow continues beyond the first basin, and the arrow on the CMB map does not stop at our preferred labels. Farther out lies the Shapley concentration, a massive assembly of clusters that exerts a strong pull across a huge volume. As distance measurements improved and catalogues deepened, Shapley's role grew, explaining part of the motion once attributed to a nearer attractor. So the tug is a sum of structures across scales, not a single hidden object waiting behind dust. Nearby overdensities contribute a local gradient, while more distant concentrations add a broader tilt, like a slow lean in the floor. Voids also matter because underdense regions effectively push by, offering less gravitational resistance, shaping the flow by subtraction as much as by attraction. This is how below changes meaning at cosmic scale, and why the chapter keeps returning to orientation. Below the Milky Way's plane is not only our halo's unseen mass, and it is not only a direction on a star chart, it is also the direction where our own galaxy blocks the view of the external gravitational landscape, turning a physical pull into a visual mystery. Now connect that landscape back to the central question, because the stakes are about orientation and fate, not just catalogue entries. What is truly above and below the Milky Way from our solar system's point of view, when the reference frame itself is moving? Above can be a direction of high-energy flashes, while below can be a direction of hidden pull, and both are real in different senses. The Great Attractor story shows that below is not emptiness, it is a vector, and vectors have consequences. It is the direction of our motion through the CMB rest frame, translated into a path through the cosmic web, and it is measurable in multiple ways. It is a reminder that our future sky is not only what we see, but where gravity carries us, slowly but persistently. The chapter's tension is that we infer mass where we cannot look directly, and we do it with tools that have limits. The zone of avoidance hides galaxies, and dark matter hides itself everywhere, even where the sky is clear. We build the case from indirect evidence, then test it with better surveys and better statistics, tightening the story without removing its shadows. Modern reconstructions use all-sky infrared catalogues, HI surveys, and cluster databases to reduce the blind spot and to anchor the density field. They also use peculiar velocity surveys to measure flow directly, not just density, because motion is the more honest witness. The result is a more complex, more accurate map with multiple contributors and fewer myths, and with uncertainties stated rather than concealed. Still, the mystery tone remains because the map is never complete, and the universe is not obligated to be convenient. Distance errors propagate into flow fields, and selection effects shape what we think we see, especially near the plane. Even with modern data, the cosmic web's mass is dominated by dark matter we infer, not observe, and inference always leaves room for revision. Now bring in one more layer of consequence, because motion changes exposure over long times, even if the change is imperceptible on human scales. In Chapter 5, risk depended on geometry and proximity in a cosmic shooting gallery, where rare events matter. In Chapters 6 and 7, gravity sets the trajectory that determines which neighbourhoods become near, and which structures dominate our long-term environment. The Great Attractor is not a threat, but it is a steering wheel, and it tells us something unsettling about our intuition. It tells us that our galaxy is not drifting aimlessly, and that the universe's preferred directions in motion, even if it has no preferred centre. The dipole points, the galaxy's stream, and the Milky Way's plane hides part of the evidence, forcing us to trust physics over appearance. This is another correction to the night sky illusion, and it pushes toward the climax with a quiet insistence. The sky looks symmetric, but our motion is not, and symmetry breaks the moment you measure it. The universe is not a static dome, it is a field of gradients, and we are sliding down one of them, guided by mass we mostly cannot see. Transition. Gravity does not only pull matter, it bends light, and light can reveal mass without seeing it. The same potential that steers galaxies also warps the paths of photons, leaving distortions that act like a natural experiment. To see the unseen with fewer assumptions, we will use the universe's own distortions as a measuring tool. Next, We shift from velocity fields to warped images, and the visuals will change with the method. We follow gravity's fingerprint on photons because lensing can map mass even in the dark, and it does not require galaxies to be bright. The tug becomes a pattern in light, and the cosmic detective story gains a new kind of evidence. Above and below the Milky Way feel like empty directions, yet gravity gives them structure and consequence. From the solar system, those directions cut through a three-dimensional mass field, mostly invisible, yet constantly shaping our path. When we look away from the bright disk, the sky seems to thin out, but the gravitational landscape does not. It continues, layered and extended, reaching far beyond the last obvious stars. Chapter 7 followed the tug through intergalactic darkness and ended with a promise. Gravity does not only pull matter, it bends light, and light can reveal mass without seeing it. That promise matters because our eyes are biased toward what shines, while the universe is not. If most mass does not emit, then we need a method that does not depend on glow. Start with the core idea in plain terms, because the concept can sound abstract at first. Mass curves space-time, and space-time tells light how to travel, even when the light itself has no mass. A photon still moves straight in its own local frame, yet the path looks bent to us. In everyday language, gravity changes the geometry of the route, not the speed limit of the traveller. In Einstein's picture, gravity is not a force reaching out through space like an invisible hand. It is the shape of space-time itself, warped by energy and mass, then followed by everything that moves. Light follows the straightest possible path through that curved geometry, a path called a geodesic. The bending is small near a star, larger near a galaxy, and dramatic near a cluster that contains 1 trillion suns worth of matter. This is not science fiction, and it is not a special property of black holes alone. Any mass can deflect light, from a star to a galaxy to a cluster, because every mass changes the metric. The effect is usually tiny, but the universe provides enormous lenses. A single galaxy cluster can act like a natural telescope, magnifying, stretching, and sometimes duplicating objects that would otherwise be too faint to detect. There is also a crucial point hidden inside that word, deflect. The light is not pushed sideways by a mysterious pressure, and it does not curve because it feels gravity like a stone does. It curves because the shortest path between 2 points is different in curved space-time than it is on a flat plane. That is why lensing is so powerful as evidence. It is geometry made visible. Explain gravitational lensing as a measurement, not a miracle, because the method is disciplined and testable. If we know what a background object should look like on average, distortions reveal the intervening mass. The lens is dark or bright, but the geometry still records its weight. What changes is not the source itself, but our view of it after the light has crossed a gravitational field. In practice, lensing is a comparison between expectation and observation. Galaxies in the distant universe have random orientations, so their shapes should average out to no preferred direction. When a foreground mass slightly stretches them in a coherent way, the randomness becomes patterned. That pattern is the signature, and it can be turned into a map. Separate strong lensing from weak lensing, because the chapter needs both scales and both moods. Strong lensing is obvious and rare, producing arcs, rings, and multiple images that look almost like deliberate artwork. Weak lensing is subtle and common, producing small shape changes that require statistics. One is a spectacle, the other is a census. Strong lensing appears when alignment is tight and the gravitational field is steep, so the geometry becomes extreme. The lens creates multiple light paths that arrive from different directions, as if the universe offered several corridors at once. Sometimes those paths form a near-perfect circle, an Einstein ring when the alignment is especially precise. When the alignment is imperfect, the ring breaks into luminous arcs, thin crescents of a background galaxy stretched across the sky. The multiple images are not just copies, and they are not all identical in brightness. Each image samples a different part of the gravitational potential, so each carries a slightly different distortion and magnification. Time delays between images can even encode the potential and the distance scale. If the background source varies, we can watch the flicker echo from one image to another, gravity turning the cosmos into a delayed broadcast. Historically, this was not always obvious to astronomers, even after Einstein predicted it. Early confirmations, like the 1919 eclipse measurements of starlight deflection by the Sun, were small and controversial in their precision. Later, the discovery of lensed quasars and giant arcs made the phenomenon unmistakable. With modern telescopes, strong lensing became not only a test of relativity, but also a practical tool for weighing the invisible. Weak lensing is the quiet workhorse, and it matches the tone of unseen scaffolding. Most galaxies are slightly stretched, not dramatically duplicated, and the change is smaller than the blur of the atmosphere or a camera's optics. The signal is buried in intrinsic galaxy shapes, so surveys average over millions of sources. That averaging is not a trick. It is the only way to make a tiny, coherent effect rise above cosmic noise. Weak lensing also demands careful honesty about measurement. Telescopes distort images, detectors have subtle biases, and even the atmosphere can imprint patterns that mimic shear. So lensing surveys build elaborate calibrations, simulations, and cross-checks, because the science depends on controlling those systematics. The reward is that, once corrected, the remaining pattern is gravity itself. Introduce cosmic shear as the statistical map of mass across the sky, because it turns weak lensing into a cartographic project. Large-scale structure imprints a coherent pattern of tiny alignments, like grass bent by a prevailing wind. When you stack those alignments, you reconstruct a projected mass field, including dark matter. It is a map drawn not with light, but with the way light has been nudged. Cosmic shear is also a snapshot of the cosmic web in action. Filaments, nodes, and voids do not merely arrange galaxies, they guide how matter clumps over time. The shear field traces where gravity has been strong enough to pull matter together and where it has been weaker. In other words, it sketches the skeleton that the luminous universe drapes itself over. Make the stakes explicit for the central question, because above and below is not poetic decoration. Above and below are not just starport directions away from the disk. They are lines of sight through different columns of mass, and lensing can measure those columns. In a universe where light misleads, the direction that looks empty can still be heavy. Now build the evidence chain for dark matter, because lensing is one link, not the whole case. The argument is cumulative, and it survives because independent methods converge. Each method has different systematics, yet they point to the same missing mass. If one technique were flawed, the others would not so neatly agree. Return briefly to rotation curves, because Chapter 6 established the halo as a gravitational requirement. Gas and stars orbit too fast in the outskirts for visible matter alone, and the speed stays high where the light falls off. In Newtonian terms, the mass inside the orbit must keep rising with radius. The simplest explanation is an extended halo of non-luminous mass, wrapping the galaxy like a vast unseen atmosphere. The key point is the mismatch between where the light is and where the gravity seems to be. Stars concentrate in disks and bulges, while the inferred mass extends far beyond them. This is not a small discrepancy that can be patched by a few dim stars. It is a structural difference, as if the galaxy's luminous body is only the bright core of a much larger entity. Add the next rung in the chain, which predates modern lensing surveys in spirit. In clusters, galaxies move with high-velocity dispersion, as if trapped in a deep potential. The visible galaxies and gas cannot supply that binding mass. This logic goes back to early 20th century astronomy, when clusters first revealed that light alone could not explain motion. Clarify what velocity dispersion means, because it is a lensing cousin in logic. Faster random motions require more gravity to keep the system bound, otherwise the members would escape. If the mass were only luminous, the cluster would fly apart. The dispersion is like a temperature for motion, and a hotter system demands a deeper gravitational well. Now, bring in hot gas, because clusters are not just collections of galaxies scattered through darkness. Most ordinary matter in clusters sits in a thin plasma, heated to tens of millions of degrees by infall and shocks. It glows in X-rays, and its temperature traces the depth of the potential. When we see that X-ray glow, we are seeing baryons under extreme conditions, atoms stripped into ions, moving fast enough to radiate at high energies. X-ray gas provides a second mass estimate through hydrostatic equilibrium assumptions. Pressure gradients balance gravity in a relaxed cluster, so the gas profile implies a mass profile. When clusters merge, that assumption fails, and the failure becomes evidence. The gas sloshes, shocks, and forms sharp edges, visible scars that mark a violent gravitational encounter. Transition to the key case study that ties these strands together, because a merger is where the components separate. In a collision, different components behave differently, and their separation becomes a natural experiment. Galaxies are mostly empty space, so they pass through one another with few direct hits. Gas is collisional, so it rams, heats and slows, leaving a bright, shocked wake. Introduce the bullet cluster as the cleanest public-facing example, while keeping the claim precise. Two clusters pass through each other at high speed, turning a slow cosmic drift into a rare, readable event. The hot gas collided and slowed, while galaxies mostly passed through. In X-ray images, the gas looks like a luminous bullet with a bow shock, an arrowhead of plasma cutting through a larger cloud. The decisive step is the lensing mass map because it does not care what glows. Weak lensing shows the dominant mass peaks aligned with the galaxies, not with the X-ray gas. Most of the mass behaved as if it were collisionless, moving through the impact with minimal drag. The map is not drawn from brightness, but from the subtle stretching of background galaxies behind the cluster. State the inference without overstating certainty about particle physics, because evidence has a boundary. If most mass were ordinary gas, it would lag with the shocked plasma, and the lensing peaks would sit on the X-ray glow. Instead, the mass stayed with the collisionless component, implying a dominant dark matter contribution. The simplest reading is that most of the cluster's gravitating matter does not interact strongly with itself or with gas. Acknowledge that alternatives exist, because the documentary must hold the line between evidence and interpretation. Modified gravity ideas try to explain dynamics without dark matter, changing the rules rather than adding unseen mass. Merging clusters with mass-gas separation make that harder, because the lensing signal tracks mass where little baryonic matter remains. The question becomes sharper. If gravity is modified, why does the lensing map still behave as if an invisible component moved with the galaxies? Now connect lensing back to the earlier gamma-ray thread, because the audience has been warned about confusing backgrounds. Gamma rays can hint at dark matter through annihilation or decay, but astrophysical sources can mimic faint glows. Lensing does not care about emission mechanisms, so it anchors the mass distribution independently. It is a way to say, whatever the light is doing, this is where the weight is. This is another correction to the night sky illusion, and it has a philosophical edge. Light is not a reliable proxy for weight, and emptiness is often just invisibility. The universe can be heavy where it looks quiet, and it can be bright where it is relatively light. Once you accept that, the sky becomes less like a picture and more like a field report. Shift from clusters to the Milky Way, because the chapter title promises above and below our own disk. We cannot lens our own halo the way we lens a distant cluster, because we sit inside the lens. We instead use internal traces that move through the halo like test particles. Their motions are the handwriting of the potential, written over millions and billions of years. Start with stellar streams, because they are long, cold structures that remember gravity with unusual fidelity. Streams form when a globular cluster or dwarf galaxy is tidally disrupted, pulled apart by differential gravity. The debris stretches along the orbit, tracing the potential over tens of kiloparsecs. In wide-field images, streams appear as faint, thread-like overdensities, almost like smoke trails drawn across the halo. Explain why streams are powerful in one sentence with backbone cadence. A stream is not just a line of stars. It is a dynamical record of how the halo pulls, twists and precesses over time. Each segment carries timing information, because stars stripped earlier drift farther along the orbit. In that sense, a stream is both a structure and a history. If the halo were perfectly spherical, stream tracks and precession would follow a simpler pattern, and orbital planes would remain more stable. If the halo is flattened or triaxial, the stream plane can wobble and fan, producing offsets between leading and trailing arms. Small perturbations from subhalos can also create gaps and density variations. Those gaps are not just missing stars, they are potential footprints of otherwise invisible clumps. Name a few iconic streams without turning the chapter into a catalogue, because the examples should serve the concept. Sagittarius is the giant example, wrapping around the galaxy and sampling a wide range of radii. GD1 is thinner and colder, making it sensitive to small-scale structure. In both cases, the stream's geometry becomes a constraint, like a ruler laid across the halo. Streams constrain the halo's shape, but they do not deliver a single clean answer, and that uncertainty is part of the story. Different streams probe different regions and times, and the disk and bar also perturb orbits. Uncertainties in distances proper motions and the Milky Way's time-varying potential propagate into halo inferences. Even the Sun's own motion and position inside the disk become part of the calibration because our viewpoint is not neutral. Now add satellite galaxy motions as a complementary probe because the halo extends far beyond the bright disk. Dwarf galaxies orbit in the outer halo and respond to the total mass enclosed, including matter we cannot see. Their velocities, combined with distances, constrain the Milky Way's virial mass. The satellites are sparse and unevenly distributed, but each one is a dynamical test, asking how deep the galaxy's gravity well really is. Make the uncertainty explicit because the mystery deepens when numbers refuse to settle. Estimates of the Milky Way's total halo mass vary by factors near 2, depending on traces and assumptions. The outer halo is hard to weigh because we sit inside it. It is like trying to measure the size of a forest while standing among the trees, with only partial sightlines to the edge. Introduce the concept of triaxiality carefully, because it reframes above and below as directions through a 3D field. The halo may be elongated, not perfectly round, and its axes may not align with the disk. That means the gravitational environment above the plane can differ subtly from below, even if the starlight looks symmetric. A slight elongation can change orbital precession rates, stream thickness, and the way satellites cluster in their trajectories. Bring in the hot circumgalactic medium, because the halo is not only dark matter, and baryons do not vanish. A large reservoir of ionized gas surrounds the disk, traced by X-ray emission and UV absorption lines against distant quasars. It is thin and hot, and it carries baryons that never became stars. The gas is difficult to image directly, but it reveals itself in shadows, absorption features that mark its presence along specific sight lines. Connect this to earlier chapters about outflows and high-latitude structures, because the halo is a stage for feedback. The Fermi bubbles and X-ray arcs imply energy injection into the halo, likely from star formation or activity near the central black hole. That energy moves through a medium shaped by the halo's gravity, and gravity sets the scale height of hot gas. The bubbles rise because they are overpressured, yet their expansion and confinement still depend on the surrounding mass distribution. Now explicitly reframe above and below in the chapter's terms so the title feels earned. Above and below the disk are not opposite voids, they are opposite directions through the same halo. The disk's stars dominate the light, but dark matter and hot gas dominate the mass budget away from the midplane. When we look up out of the plane, we are looking into the galaxy's extended body, not out of the galaxy entirely. State the key geometric claim in a disciplined way, because clarity matters more than drama here. The Milky Way halo is roughly spheroidal on large scales, so its pull is similar above and below. Near the plane, the disk adds a strong vertical restoring force, but the halo sets the long-range background. In effect, the disk shapes local vertical motion, while the halo shapes the broader orbit and the escape speed. This matters for our trajectory, because we oscillate through the plane while orbiting the center, and those oscillations are not perfectly gentle. The restoring force near the disk is baryon heavy, but the deeper channel is dark matter. Over millions of years, our path is guided by a component we cannot see. The Sun's motion is a kind of slow vibration within a larger gravitational instrument, and the halo is the resonant body. Return to lensing as the universal method that makes this story bigger than the Milky Way, because it scales beyond our local limitations. In distant galaxies, lensing maps halos directly in projection, letting us compare mass and light across cosmic environments. In clusters, lensing maps mass where light and gas disagree, and the disagreement becomes evidence. The method is the same, but the targets change, from individual halos to the architecture of the universe. Explain how lensing becomes a three-dimensional reconstruction, because the chapter promises a 3D mass field rather than a flat sketch. With redshifts, we place sources at different distances and perform lensing tomography, comparing shear signals in successive background layers. That turns a flat map into layered slices of mass across cosmic time. The result is not a perfect 3D photograph, but it is a constrained reconstruction, built from geometry and statistics. Cosmic shear surveys become a kind of gravitational cartography, and the visuals can feel almost medical in their precision. They measure how structure grows, how matter clusters, and how the cosmic web thickens as the universe evolves. The result is a map of where gravity is strongest, even when the matter is dark. In those maps, filaments appear as faint ridges of convergence, and voids appear as broad basins where the shear field relaxes. Tie the method back to the Great Attractor theme without repeating Chapter 7, because the audience needs continuity, not redundancy. Velocity flows infer the slope of the potential from motion, reading gravity through how galaxies drift. Lensing infers the potential from distorted light, reading gravity through how photons are redirected. When both methods point to the same hidden landscape, the case becomes sturdier, because the universe is being interrogated in two different languages. Now deepen the mystery with one clear statement about composition, because mapping is not the same as understanding. Most of the matter shaping our orbit is not made of atoms, and it does not participate in chemistry or starlight. We can map its distribution with increasing precision, yet its particle nature remains unknown. That gap between where it is and what it is one of modern science's most persistent tensions. Acknowledge the frontier without turning this chapter into the particle chapter, because the narrative must stay focused. Candidates range from weakly interacting particles to axion-like fields, and experiments search in labs and in space. For now, the documentary stays with what the sky itself forces us to accept, which is mass without light. The restraint is important, because the evidence is astrophysical, even if the answer may be microscopic. Bring back the documentary's tone by returning to fingerprints, because the unseen still leaves marks. Dark matter does not glow, but it leaves arcs, shears, and velocity patterns that can be measured and compared. It separates from hot gas in collisions, and it holds galaxies together where starlight fades. The fingerprints are consistent across scales, from the outskirts of spirals to the cores of clusters. This is another correction to the night sky illusion, and it raises the stakes for the finale. The most important structure above and below the Milky Way is not what shines. It is what pulls, and it pulls everywhere. The darkness is not empty, and the quiet is not weightless. Now prepare the transition promised by the chapter description, moving from scaffolding to substance without breaking the mood. If gravity is the framework, what is the material flowing along it? What fills the halo, and what cycles between the disk and the space above and below? The map of mass tells us where the channels are, but it does not yet show what is moving through them. The next step is to follow the ordinary matter as it responds, heats, cools, and circulates. End on a forward pull that points to the next chapter's theme, because the story is about motion as much as structure. We have mapped the unseen weight that shapes our route, and we have learned to distrust light as a guide to mass. Next, we follow the baryons that respond to that weight, tracing inflow, outflow, and the galaxy's long breathing cycle. Above and below will stop being directions on the sky and become pathways in a living system. Above and below the Milky Way, the night looks calm, but the galaxy is exchanging matter. The disk is not a closed city of stars, and the halo is not empty air. Between them is a working boundary layer where heat, radiation, and gravity negotiate every cycle. In wide-field images, the starlight seems fixed, yet the gas is restless, threaded, shredded, and rebuilt on timescales longer than a civilization. Chapter 8 mapped the unseen weight that shapes our route through the halo. Now we follow the ordinary matter that responds to that weight, and sometimes fights it. Gas rises from the disk, cools in the halo, and returns as rain. Some gas escapes, some arrives from outside, and the balance sets the pace of star formation. If the galaxy is a machine, this is its intake and exhaust, and the gauges are written in spectra. This is another correction to the night sky illusion. The Milky Way is not a static band with quiet poles. It is a breathing system, and the breath leaves signatures in gamma rays, radio maps, and polarized light. Even the empty high latitudes can glow faintly, because thin plasma and fast particles still radiate. Start with the engine in the disk, because the fountain begins where stars die. Massive stars end as supernovae, and their shock waves dump energy into surrounding gas. A single blast can drive a shock front for tens of parsecs, heating gas to millions of Kelvin and ionizing what it touches. The interstellar medium becomes a patchwork of hot bubbles, cold clouds, and turbulent interfaces. In clustered regions, multiple supernova overlap, building superbubbles that punch upward through the disk. On screen, the disk becomes a layered cross-section. Dark dust lanes below, bright star-forming knots within, and a frothy, glowing skin above. The galactic fountain model is simple in outline and complex in detail. Hot gas is launched upward by feedback, expands into lower pressure, and rises into the halo. As it climbs, it cools by radiation and mixing, and it can condense into cooler clumps. That cooling is not just losing heat, it is atoms and ions shedding energy in specific lines, like neon signs in the ultraviolet. Gravity then pulls that cooled material back toward the plane, returning metals and mass to the star-forming layer. The arc is elegant, but the flow is messy, full of vortices, shocks, and shear. The fountain is not a single plume, and it is not perfectly symmetric above and below. It is many local chimneys, driven by where star formation happens now, and where it happened millions of years ago. The disk's spiral structure matters, because spiral arms concentrate massive stars and therefore concentrate feedback. The result is a time-variable, patchy circulation that the sun moves through. If we could speed up time, the halo would look like weather, with fronts and squalls rising from luminous neighborhoods. Supernova feedback does more than move gas, it changes chemistry in future generations. Metals forged in stars are ejected into the hot phase, then carried upward and outward. When that enriched gas returns, it seeds the disk with cooling agents that help new clouds collapse. In plain terms, heavier elements help gas radiate energy away, so it can become cold enough to form stars. The fountain is therefore a regulator, because it both suppresses and enables star formation depending on phase and location. It is also a memory. Each cycle carries the chemical record of earlier stellar lives. The key tension is that star formation needs cold, dense gas, yet feedback heats and disperses it. If feedback is too weak, gas collapses too efficiently and burns out quickly. If feedback is too strong, the disk is starved and the galaxy fades. The Milky Way's present state implies a long-lived balance maintained by cycling and replenishment. That balance is not a single number, it's a moving compromise, renegotiated as spiral arms drift and stellar populations age. Now separate speculation from evidence, because the documentary must hold that line. We cannot watch the entire fountain in real time, but we can measure its traces. Each wavelength sees a different temperature and density, and together they outline the flow. The trick is to treat the sky like a layered medical scan, where each band reveals a different tissue. Radio observations reveal neutral hydrogen, and the 21-centimeter line maps cold and warm HI. That line is a hyperfine transition, a tiny flip in hydrogen's ground state that becomes powerful only because hydrogen is everywhere. Above the plane, HI appears as discrete clouds moving at unusual speeds. These high-velocity clouds do not follow simple disk rotation, and their velocities hint at halo orbits, infall, or outflow. Some are nearby and interacting with the disk, while others may be farther and more pristine. Visually, they appear as pale, drifting islands in a sea of faint emission, each with a Doppler-shifted signature. High-velocity clouds matter because they can be fuel, not just debris. If they are infalling, they deliver fresh hydrogen that can become future stars. If they are fountain return flow, they recycle enriched disk material back into the star-forming layer. The critical question is origin, and origin is tested by distance, metallicity, and ionization state. In practice, each test is partial, so the answer is often a probability, not a verdict. Distances are hard because clouds have no built-in yardstick. Astronomers bracket distances using absorption against stars at known ranges, looking for cloud fingerprints in stellar spectra. If a star shows the absorption, the cloud is in front of it. If it does not, the cloud may be behind, and the bracket tightens with more targets. This method is painstaking, and it echoes older astronomy, using background lights as rulers when direct measurement fails. Metallicity is the chemical clue that separates imported gas from recycled gas. UV absorption lines against background quasars measure ions like Cis2, C2, and O6. Low metallicity suggests extragalactic infall or long-isolated halo gas. Higher metallicity suggests disk origin, consistent with a fountain that carries enriched material upward. Historically, these ultraviolet techniques matured with space telescopes. Because Earth's atmosphere blocks the very lines that carry the halo's secrets, the UV also reveals interfaces where hot and cool phases meet and mix. OVICE traces gas near a few 100,000 Kelvin, a temperature that often marks turbulent mixing layers. Those layers are where cooling can accelerate and where condensation can begin. In that sense, the UV is not only a chemical probe, it is a phase change probe. The halo is not neatly layered. It is stitched together by these unstable boundaries. X-rays extend the story into the hottest halo component. Diffuse soft X-ray emission traces million-degree plasma in the circumgalactic medium. Absorption lines of O7s and O8 against bright background sources reveal hot gas even when emission is faint. These measurements suggest a massive extended reservoir that may hold a large fraction of the Milky Way's missing baryons. If that reservoir is real and widespread, it changes the galaxy's accounting, how much ordinary matter is present and where it hides. Yet the X-ray halo is difficult to interpret because foregrounds confuse the view. Local hot gas, solar wind charge exchange, and unresolved point sources can mimic diffuse glow. This echoes Chapter 3's warning about confusing backgrounds in gamma rays. The method is the same across bands, because subtraction and modelling decide what remains. The halo, in other words, is revealed as much by careful skepticism as by sensitive detectors. Now connect the fountain to the larger ecosystem, because the halo is not only a sink. The Milky Way is embedded in the local group environment, and gas can accrete along filaments. Some in full may arrive as warm ionized streams rather than cold HI clouds. The galaxy's growth depends on this slow supply, because star formation over billions of years requires replenishment. In simulations, these flows look like faint rivers feeding a rotating basin, and the basin is never truly sealed. Accretion is therefore the counterbreath to feedback. Outflows carry mass and energy away from the disk, while infall brings new mass in. The net star formation rate is a bookkeeping problem, balancing consumption, recycling, and supply. If the supply fails, the disk gradually runs down, even if feedback is perfectly tuned. The mystery is not weather gas cycles, but how efficiently each phase hands off to the next. The Magellanic system becomes a nearby case study of gas exchange. The Magellanic Stream is a long ribbon of gas trailing the large and small Magellanic Clouds. It is shaped by tides, ram pressure, and the Milky Way's halo medium. Parts of it may eventually feed the disk, while other parts may be shredded and mixed into the halo. In a wide, slow pan, the stream reads like a brushstroke across the sky. Evidence that galaxies trade matter even when they never collide. Now add the non-thermal component, because gas alone does not set the pressure budget. Cosmic rays carry energy comparable to thermal gas in parts of the interstellar medium. They are charged particles, so they couple to magnetic fields and scatter on plasma waves. That coupling lets cosmic rays push on gas over large distances, even where the gas is too thin for ordinary pressure to matter. The physics is subtle. The particles stream, excite waves, and then ride the very turbulence they create. An invisible feedback loop. Cosmic rays are also the bridge back to gamma rays, because they make the high-energy sky glow. When cosmic ray protons hit gas, they produce pions that decay into gamma rays. When cosmic ray electrons scatter starlight and infrared photons, they produce gamma rays by inverse Compton emission. The gamma ray sky is therefore a map of both particles and targets, and it is sensitive to where the halo contains gas and radiation fields. In visual terms, it is a shadow play of collisions drawn on a canvas we cannot see with our eyes. This is where the Fermi bubbles return as a central clue. Their hard gamma-ray spectrum and sharp edges suggest organized transport or confinement. If the bubbles are driven by a past nuclear outflow, then the Milky Way has recently exhaled energy far above and below the plane. If they are driven by a starburst wind, then clustered supernovae in the center can also power a large-scale breath. Either way, the geometry is telling. Two lobes, aligned with the minor axis, like a signature stamped into the halo. Magnetic fields shape this story because they guide charged particles and suppress cross-field diffusion. Polarization and Faraday rotation measure field geometry and strength along lines of sight. Draped fields at bubble edges could help maintain sharp boundaries and could trap cosmic rays long enough to sustain emission. The bubbles therefore become a laboratory for transport physics, not just a relic of an eruption. When the map overlays polarization vectors on gamma-ray contours, the galaxy starts to look engineered, even though it is not. The unresolved questions from Chapter 4 sharpen here, because the breath needs a driver and a clock. How old are the bubbles, and how fast did their contents travel? Did cosmic rays ride an advecting wind, or diffuse through a turbulent halo? Are the gamma rays leptonic, implying energetic electrons and strong radiation fields, or hadronic, implying dense targets and neutrino production? Each question is a fork in the story, and each fork points to a different physical regime. Each option predicts different multi-wavelength companions and different energy budgets. A hadronic model demands enough gas in the bubbles to make collisions efficient, and it predicts neutrinos at some level. A leptonic model demands electron acceleration and survival against cooling, and it predicts synchrotron haze tied to magnetic fields. The documentary does not pick a winner yet because the evidence is still converging. In science, restraint is not hesitation. It is the discipline that keeps a mystery solvable. Now widened from the galactic centre to the whole disk, because winds are not only central. Star-forming regions across the disk drive local outflows that merge into a patchy halo circulation. In external galaxies, we see bipolar winds aligned with minor axes, especially in starbursts. The Milky Way is harder because we observe from inside, but the same physics should apply. Our disadvantage in perspective is also an advantage in detail, because we can sample the local medium directly. Cosmic rays can help launch these winds by providing pressure that does not cool quickly. Thermal gas can radiate energy away, especially when it becomes denser. Cosmic ray pressure can persist, pushing on gas through magnetic coupling and driving a gentler long-range acceleration. In that picture, the wind is not only hot plasma, it is a multi-phase flow with cold clumps embedded in a hotter magnetized medium. Those clumps may survive by shielding and rapid cooling, or they may evaporate into a trailing mist. Either outcome changes what returns to the disk. The fate of outflowing gas depends on gravity, which brings Chapter 6 back into the breath. If the outflow speed stays below escape velocity, the gas will stall and return as a fountain. If it exceeds escape speed, it can leave the halo and enrich the circumgalactic and intergalactic medium. The Milky Way's halo mass sets that threshold, and the threshold can vary with direction if the potential is not perfectly spherical. A small change in speed can decide between recycling and loss, and the galaxy's future is built from those marginal outcomes. This is where above and below become more than geometry. Above and below are the directions where the disk's restoring force weakens, and where the halo becomes the main gravitational guide. They're also the directions where large structures like the bubbles can channel flow. The galaxy's breath is therefore anisotropic, shaped by the disk, the bar, and the magnetic scaffold. In the visuals, streamlines bend, flare, and then curl back, like smoke meeting a ceiling. Now bring the Sun into the system, because the central question is anchored to our viewpoint. We orbit the galactic center and oscillate through the plane over tens of millions of years. That motion changes our local environment, even if the changes are subtle on human timescales. The solar system samples different densities, magnetic conditions, and cosmic ray backgrounds as it drifts. What looks like a stable night sky is, for the heliosphere, a changing climate. Radiation exposure is not constant, and that variability is part of what lies above and below. Spiral arms contain more supernova remnants, more massive stars, and more turbulent fields. Superbubbles carve cavities that can lower local gas density and alter cosmic ray confinement. Local cavities can reduce shielding and change how cosmic rays and gamma rays propagate through our neighborhood. A quiet region is not necessarily safe, and a bright region is not necessarily dangerous. The details depend on geometry and timing. The local bubble is a nearby example of an excavated region, likely shaped by past supernovae. It is a low-density cavity with hot gas and complex boundaries. Its existence implies that the Sun's recent path has been through a disturbed medium, not an average slice of the disk. That matters for heliosphere size, cosmic ray modulation, and the background against which we interpret diffuse emission. In a rendered fly-through, the bubble's walls appear as a faint irregular shell, like the edge of a blown glass sphere. Gamma ray exposure also depends on where cosmic rays are produced and where they interact. If we pass near dense clouds, pion-producing collisions increase, and gamma ray brightness rises. If we pass through cavities, targets are fewer, and the gamma ray glow can drop even if cosmic ray density stays high. The sky we measure is therefore a convolution of particle distribution, gas distribution, and radiation fields. The question becomes almost philosophical. Are we seeing the galaxy as it is, or as our location forces it to appear? This returns to the Chapter 3 thread about unidentified gamma ray sources and diffuse confusion. Some apparent excesses can be unresolved pulsars, remnants, or structured gas templates. Some could trace genuine changes in cosmic ray density or transport, tied to winds and fountains. The breath complicates interpretation because it makes the foreground dynamic and structured rather than smooth. A map can be accurate and still be misleading if the model behind it is too simple. Now address the risk thread without turning it into the GRB chapter again. Chapter 5 framed gamma ray bursts as directional hazards, rare but potentially catastrophic. The breath does not create GRBs, but it changes the background in which we estimate and interpret risk. It changes where massive stars form, where remnants concentrate, and where shielding gas accumulates. Even a modest change in local gas density can alter how radiation and particles reach us. On long timescales, our trajectory through arms and interarm regions changes the odds of nearby explosions. It also changes the probability of encountering dense clouds that could compress the heliosphere. These are not clean periodicities, and the geological record is messy and confounded. The honest claim is variability, not metronome, and the uncertainty must remain explicit. The deeper question is uncomfortable. How much of Earth's long history is shaped by astrophysical chance rather than terrestrial cause? Now connect the breath to hidden gravity again, because matter flow depends on the potential. The halo's mass distribution sets the scale height of hot gas and the confinement of cosmic rays. A deeper potential holds onto more baryons, increasing recycling and reducing escape. A shallower potential leaks more material, changing metallicity evolution and long-term star formation. In that sense, dark matter is not just a missing ingredient. It is the container that decides what the galaxy can keep. The circumgalactic medium becomes the reservoir where these outcomes accumulate. It stores ejected metals, receives accreted hydrogen, and mediates mixing. It is also the medium through which the Fermi bubbles expanded and through which future outflows will propagate. In that sense, the halo is not only a gravitational scaffold, it is a working atmosphere. If we could see it directly, it might resemble a faint aurora around the entire galaxy, structured, layered, and alive. The breath also shapes magnetic topology, because outflows stretch and lift field lines. Lifted fields can guide cosmic rays into the halo, changing where gamma rays are produced. Infalling clouds can drape fields and create wakes, changing turbulence and reconnection. The ecosystem is coupled, and no single component can be treated as a passive tracer. Every map we draw is a snapshot of a system that is still negotiating its own boundaries. Now make the chapter's central synthesis explicit, because this is the climax beat. Gamma rays trace cosmic rays and collisions, revealing where high-energy particles roam. Magnetic fields guide those particles and transmit pressure into thin gas. Gravity sets the boundary conditions, deciding what returns, what escapes, and what remains suspended above and below. The three together form a closed argument, yet the numbers inside that argument are still being measured. In this synthesis, the Milky Way is neither a serene disk nor a simple halo. It is a regulated engine, breathing through feedback and accretion. The breath sets the density and composition of the medium our solar system travels through. It also sets the background against which rare catastrophes stand out, and against which we search for faint new physics. The calm band of the Milky Way becomes, in the mind's eye, a living boundary between furnace and fog. Now sharpen what remains unknown, because the climax needs unresolved edges. We still do not know the dominant driver of the Fermi bubbles, or the exact transport mechanism that keeps their edges sharp. We still do not know the full mass and phase structure of the circumgalactic medium, or how much inflow is hidden in ionized form. We still do not know how cosmic ray pressure competes with thermal pressure across the halo, or how magnetic geometry changes with time. Each unknown is a reminder that the galaxy is not a diagram, it is an experiment still running. We also still do not know what dark matter is, even though it sets the gravitational stage. Gamma ray searches for dark matter signals must contend with the breath-structured foregrounds. A faint halo glow could be annihilation, or it could be cosmic rays in a thicker gas layer than we modelled. Disentangling those possibilities demands better maps of gas, better models of transport, and better cross-checks across wavelengths. The question is sharp. When the foreground is alive, how do we recognise a signal that does not belong to it? Transition. With the pieces assembled, radiation from above, gravity from below, we confront the central question directly. What does it mean for our future, and what remains unknown? From the solar system's point of view, above and below are not empty directions. They are pathways through a living halo where matter cycles, fields twist, and high-energy particles roam. Our past has been shaped by where we travelled in that system, and our future will be shaped by where gravity and feedback carry the next breath. The Milky Way does not promise stability, but it does offer patterns if we learn how to read them. The next chapter must resolve the story's promise without pretending the mystery is gone. We will weigh what we can predict, what we can only bound, and what could still surprise us. Above and below will become not just directions on a map, but constraints on fate in a galaxy that never stops moving. The central question returns with a final correction to the night sky illusion, because perspective can lie even when the stars look honest. Above and below the Milky Way are not empty directions, they are different columns through real structure. When the bright band thins, our line of sight stops skimming the disk and begins sampling the galaxy's outer atmosphere. Above and below the plane lies the halo and circumgalactic medium, extended and active beyond the bright disk. These regions are not a clean vacuum, but a dilute multi-temperature ecosystem threaded by fields and turbulence. They hold hot plasma at millions of degrees, cosmic rays moving near light speed, and magnetic fields that guide charged particles. They also preserve relic geometry, faint arcs, gradients, and cavities that remember earlier eruptions. Visually, the disk is a luminous river, but the halo is a dim ocean whose surface only glints in special light. In X-rays, it can glow softly, and in ultraviolet absorption it leaves fingerprints on background quasars. Those spectral notches are small, yet they reveal ionized oxygen and other traces of gas too thin to photograph directly. The Fermi bubbles remain the clearest scar, twin lobes rooted at the galactic center. They rise tens of thousands of light years above and below the plane, like lanterns lit inside a fog. Their sharp edges and hard spectrum still argue for shocks, confinement, and transport physics we do not fully control. The bubbles also force an uncomfortable clarity. The Milky Way has not been quiet, even in the recent cosmic past. Historically, we once pictured our galaxy as a mostly settled disk with a calm nucleus. Then radio surveys mapped strange filaments near the center, and gamma-ray telescopes revealed structures no optical atlas could show. The bubbles turned the halo into a stage, and they made the question unavoidable. What else is written into the dark between the stars? Gamma rays also arrive as sudden messages from elsewhere, and the universe has proved it can be violent. Bursts are rare and beamed, so catastrophe depends on distance, direction, and timing. A jet that misses us is just data, while a jet that hits us becomes chemistry and heat. Even then, the danger is not a movie explosion, but a cascade of ionization through the upper atmosphere. Risk must be stated with discipline, not dread, because probability is part of the physics. A nearby aligned GRB is unlikely on human timescales, yet the hazard is physically real. We know this because we observe the engines, measure their energies, and model how radiation couples to air. The night sky is serene, but the underlying distribution includes extremes. Earth is not defenseless, and the shields are measurable. The atmosphere absorbs much of the high-energy flux, converting it into showers of secondary particles that lose energy quickly. The magnetosphere deflects many charged particles, and its shape changes with solar wind pressure, an invisible bow shock in space. Even so, protection is not uniform because polar regions and high altitudes are more exposed. But shielding is not a guarantee, and it never was. Extreme events can overwhelm margins, and indirect effects can propagate through chemistry and climate. Ozone depletion is one example, because it changes how much ultraviolet reaches the surface long after the flash is gone. The lesson is subtle. The most important impacts may arrive late, after the sky has returned to normal. Now the story turns from flashes to the steady current that never stops. Beneath the visible sky lies gravitational architecture, dominated by dark matter and large-scale structure. Gravity is quiet, but it is relentless, and it shapes the long game of every orbit. The Milky Way's disk and bulge shape local motion, but the halo sets the long-range well. That invisible mass governs escape speed, vertical oscillations, and the outer rotation curve, where stars move too fast for visible matter alone. It also controls how satellite galaxies fall in, and how stellar streams stretch into thin, readable ribbons. Each stream is a test particle, an ancient orbit drawn out across the sky. On larger scales, the cosmic web shapes our drift through expanding space. Galaxies do not simply ride the Hubble flow, because nearby overdensities tug them into coherent motion. Peculiar velocities, lensing maps, and structure formation theory all describe the same guidance. In plain terms, we are moving through a landscape of mass we cannot see directly. This is what dragging means in a universe without friction. Gravity steadily redirects trajectories, and we can read it in motions and distorted light. Weak lensing slightly shears the shapes of distant galaxies, and that tiny alignment becomes a map of foreground mass. It is a subtle signal, but it scales up into a portrait of structure. Yet the map is incomplete, and the uncertainties matter. The Milky Way's total halo mass still varies by roughly a factor of 2 across methods. Some estimates rely on satellite motions, others on stream modelling, and others on the speed distribution of halo stars. Each method has assumptions, and each assumption leaves a shadow in the final number. The CGM is also not fully counted, and missing baryons may hide in hot, diffuse phases. X-ray emission and UV absorption suggest a reservoir, but foregrounds complicate every subtraction. Separating local gas from distant halo gas is hard, because both sight along the same line of sight. The result is a census with error bars that still feel uncomfortably wide. We also do not know the Milky Way's full eruption history. The bubbles imply recent activity, but recurrence rates and energies remain poorly pinned down. Was it an outburst from the central black hole, or a burst of star formation driving a wind, or some combination? The halo keeps the record, but it is written in faint gradients and cooling times. Even the high-energy sky still contains confusion. Unidentified gamma-ray sources and structured diffuse emission can mimic new physics if templates are wrong. A mismodelled foreground can look like a discovery, and a real signal can be buried under the wrong subtraction. Precision here is not a luxury. It is the difference between insight and illusion. Dark matter remains the deepest unknown, because mapping is not identification. Lensing, streams, and galaxy dynamics show where the mass is, not what it is. It could be a new particle, it could have weak self-interactions, or it could behave in ways that only appear on certain scales. The halo is a laboratory, but it is a laboratory without labels. Future progress is practical, and it is already planned. Better MeV and gamma-ray astronomy will separate source classes, spectra, and diffuse components. Improved angular resolution will sharpen edges, while broader energy coverage will reveal how particles are accelerated and cooled. With time domain monitoring, we also learn which sources flare and which simply glow. Next-generation all-sky surveys will refine distances and proper motions, tightening the Milky Way potential. With more accurate stellar velocities, the halo's shape and mass profile become harder to evade. Deeper lensing and cosmology projects will constrain clustering, flows, and dark matter behavior. Each dataset is a different slice, and together they reduce the room for ambiguity. Mapping the CGM will become a central frontier, not a side quest. More background sightlines and higher resolution spectroscopy will turn patchy hints into a coherent census. We will measure metallicity, temperature structure, and kinematics, how gas rotates, falls, and escapes. Those details tell us how galaxies recycle matter and how the disk stays supplied over time. Transition. With radiation from above and gravity from below, the answer becomes a synthesis. The emptiness was never empty, it was simply faint in the wavelengths our eyes prefer. Above and below the plane are gateways into two dominant realities. One is high-energy processes that flare, propagate, and sometimes threaten. The other is hidden mass that quietly shapes every orbit, every flow, and every long-term encounter. Together they explain why the emptiest-looking directions can be the most revealing. When stars thin out, the galaxy's engines and scaffolding come into view. Our solar system is a passenger in a structured, active universe, moving through a halo we're still learning to weigh. And as we refine the maps of plasma, of fields, of mass, we also refine the question that started it all. What else is present, even when the sky appears silent? We began by losing our Earth-made sense of up and down, then rebuilt it with a galactic map, a spinning disk, and a halo that only looks empty. In that dimmer sky we found violence and memory, from the Fermi bubble's sharp-edged twin scars to the needle flash threat of gamma-ray bursts. And beneath every glow we traced the quieter architect, gravity, measured in rotation curves, revealed by lensing, and extended outward into the cosmic web that steers our entire neighbourhood. Above and below the plane, the Milky Way is not a backdrop but a boundary layer, where hot gas rises, cooler gas returns, and missing baryons may be hiding in plain sight. The same columns that carry cosmic rays and gamma rays also cut through an unseen mass field, a dark halo whose shape we can sketch but whose substance still refuses a name. Even our viewpoint is part of the story, because we are off-center and slightly off the midplane, and that bias can masquerade as a symmetry until maps, motions, and multi-wavelength cross-checks separate perspective from structure. What we called quiet-looking sky turned out to be a set of instruments, each tuned to a different truth and none of them complete by itself. Gamma rays tell us where particles are accelerated and where ancient outbursts may have vented, yet diffuse backgrounds and unidentified sources keep the high-energy sky crowded with imposters. Gravity tells us where the weight is, through streams, satellites' shear and the stubborn flatness of the rotation curve, yet it cannot by itself tell us what the weight is made of. Put together, the chapters describe a living galaxy that breathes and remembers, episodically flaring at its core, continuously cycling matter through its halo, and continuously pulling us along a trajectory we can measure better than we can interpret. The unanswered threads are not loose ends so much as coordinates for the next survey. The bubble's true engine, the halo's true mass and shape, the location of the missing baryons, the disciplined statistics of rare cosmic catastrophes, and the particle identity of the dark matter that binds it all. And over it all lies a final correction to the night sky illusion, because emptiness is often just a failure of our eyes, not a property of space. When we look away from the bright band, we are not looking into nothing. We are looking into the Milky Way's working layers, its scars, its currents, and its hidden scaffolding. The question that opened this journey asked which side shapes our past, our motion, and our fate, as if above and below were opposing kingdoms. The answer is stranger and more unsettling, because both directions are active frontiers, and we live between them, bathed by rare, violent photons and steered by a constant, invisible undertow. From our solar system's point of view, above is where the galaxy sometimes shouts, and below is where it never stops whispering. Together they write the long story of where we have been and where we are being carried. If there is closure here, it is not in certainty but in orientation, because we can now name what the darkness is doing, even when we cannot yet name what it is. The Milky Way is not balanced light with blank margins, it is a layered engine, and the poles are its vents and its archives lit by radiation shaped by gravity and threaded by matter that refuses to stay put. And the most memorable truth may be this: the galaxy does not have an up or a down, it has directions of consequence, and we are learning, slowly, carefully, how to read them. So keep looking into the thin places, where starlight fades and the real structure begins, and follow the next maps as they arrive, because the frontier above and below the Milky Way is also the frontier of what we are. The Milky Way only looks balanced, but from here it is a tilted battlefield of two different forces, one that strikes in rare gamma-ray firestorms and one that pulls forever in hidden gravity. Above and below are not voids on either side of a bright river. They are columns through a living galaxy, and both are shaping our past, our motion, and our fate at once. In the end, the most dangerous illusion is not the darkness beyond the band of stars, it is the belief that darkness means nothing is there. Above and below the Milky Way, the night is not empty, it is active, and it is watching back in wavelengths and forces we are only beginning to understand. If you want to know what's truly above and below us, follow the data, support the surveys, and let the sky be measured in every colour it can speak.